So today's session, technology, will focus and will put a special emphasis on 3 different themes. One will be the charge controller. The second one will be power electronics, and the last one will be water pumping. So why do we put this emphasis on these 3 themes? Is because we have a lot of members that have done some developments in the past years on these topics. And because it's really a problem to a lot of members, we could have chosen a lot of other topics that are addressed as well by the technology working group. But today we have panelists gathered around these thematics. So the idea is that every participant and every panelist will have a time to dedicate to a small presentation. And then I hope that we will have some spare time to have some exchange between the panelists and the participants as well, to get guidelines on what are the next steps for these panels and for these thematics as charge controller, power electronics, and water pumping. And maybe to arrange a new collaborative project with new members that want to jump in these thematics and want to start sharing and associate with around these thematics. So I will just give a brief introduction to the technology working group, and then I will give the flow of speech to the charge controller panel. With the first person to intervene, who will be Hugh Piggott, the author of the Wind Turbine Recipe book. So what is the technology working group? Well, first, a bit of context. I will present who I am. I am the technology working group coordinator, and I have a really boring wind CV. So instead of going through the CV, I prefer to present my experience with small wind and also give an insight of what drives me to become the technology working group coordinator, and why I want to try to gather people around joint projects. I'm coming from Grenoble, a town in France, in the mountains, and I come from a student organization who was dedicated to build small wind turbines around education and having good projects. This was my first starter. It was terrible. It was not working at all. And at some point, we decided to bring a turbine to the field. It was a project in Morocco. We've been there with a turbine, and we were really excited to deploy a microgrid with small solar panels and a wind turbine. And eventually, we made it to light the school with a light bulb, and we were really proud of this achievement. And the thing is, the electronics we deployed there was homemade, and it failed. So we had to come back later to repair the installation. So we installed the installation, and in the meanwhile, I tried to, with a friend of mine that was from Morocco as well, to build a water pumping turbine, which was only with gears and mechanical stuff. So basically a pump that was a centrifugal pump driven directly by the turbine. It failed terribly. Also, electronics failed. So I was like, okay, so much failure. How do we do to make robust stuff? So I was willing to investigate more on electronics and to understand better what was going on in projects that were present in the field. And to do so, I jumped in wind farms. And this led me to try to make my own inverters and to meet a lot of people that were into the same quest of electronics, of new projects, and to bring new stuff to the field. So I tried making these inverters, and I needed some custom test rig to make sure that these inverters were working. And of course, it was a terrible fail. So I burned a lot of switches doing so. In the meanwhile, I met a lot of people around these thematics that were trying to do the same as me. So I met Rafael, I met Luis, I met Nasos. And so we all developed this technology together and trying to make it better up to the point we can deploy it into the field. I also met different people to improve the ideas that I had to try to pump water with these turbines. So I met with Manuel, I met with Jorge, I met with Damien. And finally, we made it to the point where we're able to pump some water in buckets. All of this is a lot of hard work trying to make things work and to the point that the technology is robust enough to be deployed on the field without the fears that it will break off 6 months after and that you have to turn back to the rural and remote place to repair everything again. So my personal experience I would like to share with everyone today, and I think a lot of people will share this constat is, well, making robust stuff is hard. And so this is what Technology Working Group is about, in my opinion. It's about sharing ideas and the need from the fields to do and to develop relevant technologies for the people that need it. But it's also about sharing the time of development and the time of troubleshooting and not being isolated doing so, and having this collaboration going on. Working together is always more fun. It's also, and most of it, I believe, is sharing the time of sustaining the technology that you are developing. Because if you are giving it a shot and developing a technology, but no one will sustain it over the long term period, no one will improve it and make it visible and improved and robust enough to be compatible with the needs that are faced by people on remote areas. So why to join Technology Working Group? Well, you can do stuff on your own in your backyard, but the thing is, doing stuff alone is always more complicated than anticipated. Doing things together is still complicated. But I believe it's worth asking around if people has not attempted the same things that you are about to attempt. I mean, everyone can try to build this stuff, but it's always good to know what is the experience of the people that tried it before you. And trust me, in general, it's way more fun to do things together and to have a beer afterward. So the Technology Working Group is focusing on multiple topics. It's not dedicated to one topic or one panel that is presented today. The Technology Working Groups deals with blade manufacturing, blade improvement. It can be composites, it can be wood, it can be 3D printed stuff. It deals with charge controller application, which is like central for wind turbines, how to improve the versions that we've developed so far and how to make new ones that are innovative and have more features for the people who need additional features. It's also make better towers cheaper. It's also developing new application for small wind turbines, both for productive uses and for agricultural applications. It deals with power conversion more broadly because the electronics is not only about the charge controller, but also about inverters and things that are always necessary to deploy together with a wind turbine. So we really try to deal with the biggest variety of topics we can and try to gather groups of interested people to join and to share developments. So what we propose is that you reach us with your project, your current idea, what you are building so far, and to start sharing pictures, to start some collaboration and first have a chat with people that are trying the same thing as you are doing, because obviously in Wind Empowerment Network, someone has tried what you are trying to do, for sure. And we will try to connect with other people that are doing the same things that you are. Then the second idea is to try to build up a worldwide team. Because if someone is doing the same things that you are trying to do, but like slightly differently, maybe it's worth investing a bit more time, clearly saying and expressing the specification for the products you are trying to address. And then it will be able to build this collaborative and worldwide team that will get support from wind empowerment. And so you will get additional visibility and maybe more ease to get some funds for your project. And then the last thing is sharing your success and find helps for your future improvements and for the maintenance of the small mistakes that you obviously have done during the development of your project, and to have like this energy and this momentum that can be beneficial for your idea and for your projects that you have developed. So as I said before, today's session will be emphasizing 3 different topics. The first one will be charge controller, and I will give the floor to Hugh, who will speak about the charge controller challenges and thematics as a really critical organ to small wind turbines. Hugh, I let you share your screen.
There. Is that it?
Yeah, it works. Yeah, perfectly.
Okay, thank you. Yeah, I'm going to talk a little bit about charge controllers for hybrid wind solar systems. Actually, my experience recently has very much been with hybrid hydro and solar systems, because I work more with hydro in terms of my desk job. My thinking tends to be more about hydro. My hands-on is very much wind. I still work a lot with small wind turbines locally. Yeah, certainly a lot of my work is around charge controllers, managing the energy that's produced by these renewable energy systems. And this may be a bit basic in the beginning, but I hope that you'll get some useful information. If I can find some way to scroll to the next slide. Maybe this one. There. Okay, so what do? Charge controllers, as distinct from the maximum power point tracking function, which a lot of them include, the real core function as a charge controller is to control the charge rate of the battery. And that goes through various stages, but it's principally done by maintaining a constant battery voltage. So if this is the timeline, the voltage in the beginning is quite low. As the voltage rises, you can just keep on charging flat out. There is no need for a charge controller. Your turbine's connected directly to the batteries. That's the bulk stage. You reach the absorption stage, and you start to limit the voltage at what's called the absorbed set point. That's a voltage which is suitable for your battery type. You do that for a period of time, and you consider the battery to be charged. Then after that, you might drop down to a float set point, which is a bit lower just to maintain the battery charge, or occasionally you might go up to a higher set point to equalize the battery if it's a flooded battery and it's not going to get damaged. You might want to hit it a bit harder with a higher voltage. So all of these stages are based around a constant voltage, maintaining a constant voltage of the battery during charge. And it doesn't mean to say the battery is 100% charged as such. It may not have got there yet, but by maintaining this constant voltage, you'll be charging it at the optimum rate. So you're going to want to keep charging it, but you're going to want to moderate the current that you're charging it with. Right, so PV charge controllers, apart from, as I say, the MPPT function, which is a big thing, but it's completely separate really. The way they work is that they essentially just throttle back the current that's coming into the battery, slow it down. And I've got a big gripe about this, that actually a huge amount of PV energy is wasted in this way, just through laziness, and also because people, I think, don't understand that they're not using the energy, because all that happens is if the battery can't absorb it, it just doesn't get used. And you don't notice anything because there's no moving parts in the PV panel. So it simply gets underused or even not used at all if the battery's completely full. So that's the way that a solar PV charger works, solar battery charge controller works. And this is not suitable for a wind turbine. If you were to disconnect the wind turbine, it'll spin much faster. And the consequences of that are that the output voltage rises very high. The load falls so that the turbine voltage rises even higher. And ultimately, you're going to damage your charge controller. This also makes a lot of noise and stress on the turbine, higher gyroscopic forces, etc., etc. And again, not using the wind energy is, to my mind, quite wasteful. It's like such a wasted opportunity to use a series charge controller that limits the current coming into the battery. So wind turbines, we connect them directly in most cases. I think that other options are going to be discussed today, and that's very exciting. But I'm not aware of any particularly viable, cost-effective, reliable solutions other than connecting the rectifier directly to the battery so that the wind turbine voltage is basically the same as the battery voltage. In the diagram, you may not be able to see it for the images of the panelists, but the negative side is connected to the battery. Positive sides go through all these fuses and ammeters to see what's going on, but basically everything's in parallel connected to the battery. And to limit the current going into the battery, we have a charge controller. In this case, it's a tri-star diversion charge controller that's diverting current into resistors to use up the surplus current and prevent it from overcharging the battery. So the controller should choose just the right amount of current to go through these resistors so that the remaining current flowing into the battery maintains the desired absorbed voltage or float voltage or whatever voltage it is. This isn't actually going to affect the wind turbine itself. It's not going to slow the wind turbine down. It's the wind turbine's not even going to know that it's happening, basically. It's just as if somebody switched on a few more lights on the system and in that way maintained the correct charge through the battery to charge it optimally and not damage it, but to make sure that it keeps on being charged. So that's the way that I do it. And you can see there are also some solar panels here. I quite like to just connect solar panels through series diodes and fuse rather than through any sort of controller. And then again, I can harvest that heat usefully in resistors for water heating via the diversion load control. The gains from maximum power point tracking on solar are quite considerable, but if you look at the cost of the electronics, they're actually quite marginal in terms of comparing it, just adding another solar panel perhaps. If you have your solar panel suitably chosen, a grid-tied solar panel generally works at about 30, 33 volts, thereabouts. That'll charge a 24-volt battery very nicely. Certainly in Scotland, it might overheat in some places and the volts might be too low, but that's another story we can talk about another day. Okay, now you've got these different types of charge controller for wind turbines. Quite often what I have seen in the sort of eBay part of the wind turbine market is to divert directly off the wind turbine, have a simple transfer relay, if you like, switches the wind turbine off the battery and onto a dump load. Better to have a dump load than just switch it off because, as I pointed out, it's going to run away. So it's a good idea to divert it onto a dump load, but the problem with that is most times when you connect it to a resistor, that's just going to act like a brake. It's going to slow the machine right down. You're not really going to get much useful power. If you're looking to have a quiet life, look after the wind turbine well, then perhaps this is a good option, but it's not actually going to be providing the power that you're using. So as soon as you do that, the battery's going to discharge, then you'll be flipping it back on, it's going to charge. So, you know, it's a bit crude. And so that's not my favorite style of charge controller. The best way to do it, in my opinion, in terms of what's best for the battery is the middle one here. Diverting, I should say, directly off the battery into a DC heater. Very often it's just a high-powered resistor that you can buy from an electronics company. Ideally using PWM to pulse width modulation to smoothly divert the exact right amount of current into the heater so that the battery is maintained at the correct voltage all the time. I'm not sure whether you can see what's happening over on the right-hand side of the screen, but what I'm showing here is that you can divert just as well off the AC side of the inverter in terms of using that energy. And it's much easier to usefully employ that energy if you do it on the load side of the inverter. You'll be able to buy low-cost water heating appliances with thermostats and all the wiring is going to be standard wiring. The control relay. So if you're wanting to use the energy for something useful, then actually diverting off the AC side of the inverter is a very good way to go. And most of the systems that I do now will employ a combination of these two modes. For reliability, you'll have the direct DC dumping off the battery, but at the same time, you'll try to steal that power, if you like, and use it for an AC load, which is doing something useful like heating water. Once your water's hot, then the thermostat can turn off and quite safely do so because you're going to have charge control function continuing on the DC side direct off the battery, maintain the safe control of the battery charge. If you're diverting off the battery, it's very important to design for reliability, make sure that your equipment's well ventilated and cooled. It should be capable of carrying all the current that the dump load can take. It's not a case of designing it for the dump load should be able to take more than the wind turbine can produce, or at least as much as it can produce. And if you have one that's oversized, you must make sure that it's capable of working full time, because sooner or later, somebody's going to connect a PV panel or a generator or something to the battery. That diversion load is going to be working full time. So very often I see pictures like this where the dump load heater is right next to the electronics or even in the same box underneath it. It's just going to cook. This is a very bad idea. You want to be putting these heaters quite a long way further away from the electronics. These are heaters. They're not just electronic components. These are generating a lot of heat energy. So you need to respect that and situate them, for example, outside the building in a sheltered location. Or if you want to make use of the heat, then build it into a proper heating enclosure, such as would be used for a domestic heating appliance, such as this one on the right. That way you can safely use it in the building to, to dry off your coat or to heat the bathroom or whatever it might be, but it needs to be properly installed and not just sitting underneath the electronics. It's pretty easy to build small analog circuits that switch on and off at 14.5, on at 14.5 and on off at 13.5, for example. That's what I relied on for a couple of decades. Nowadays, I use TriStar controllers because they're cost-effective, extremely reliable, and very smooth in operation. But I could, if I didn't have the TriStars, I'm sure I could do something comparable with an Arduino and a solid-state relay that would work really well. So it's a DIY project in that area, homebrew, locally manufactured charge controller should be quite an easy thing to develop using modern digital technology. So just quickly, that's one of my early circuits where I use a voltage comparator, a couple of op amps, switching mechanical relays, and I produced dozens of these circuit boards, and quite a few of them are still working to this day. If anyone wants the circuit diagram, I have published it, but I'm quite happy to share. And there are plenty of other projects like this on the internet that you can use. What I would say about this approach is that if you're switching loads on and off, it's much better to have multiple small loads than one great big one, because the amount of switching that goes on will be much less. As the wind increases, the load decreases, you'll be switching on and off relatively small loads. If you have a big load crashing in and out regularly, it's going to be very rough and it's going to wear out your relay. Okay, so what do I do nowadays? As I've pointed out, I like to use the power. I like to use it on the AC side of the inverter. I like to use TriStar charge controller. Very often what I'll have is solar and wind or hydro coming into the battery. goes to the TriStar controller and the DC loads. That's my primary control. Through the inverter to a device called a TriStar follower, which I think Jonathan has had experience of, might speak about some more later. This actually is triggered by the operation of the TriStar and in turn uses phase control to smoothly increase and decrease the amount of AC heat that goes into a useful heater for water heating or for space heating, wherever you like in the building. It's a lot more versatile to control where you want to put it and how hot it's going to get if you're working with standard AC wiring and AC equipment. If there's a whole lot of PV, then this could cause some embarrassment to a system that's got an under-designed diversion load. But what you can do is you simply set the absorption point of your diversion slightly higher than the PV if you don't want that to happen, if you don't want your heating on. If you do want as much heat as possible, then you would set it lower than the solar. And if you don't care which is going to come on, you could set exactly the same point so as to make sure that your battery is exactly charged in the right way. One thing's for sure, those two controllers aren't going to agree with each other, and this causes a lot of distress. But in the both experts, you know, one expert opinion is never going to be the same as another, but you can trust it. It's an expert. So I don't think you need to worry about charge controllers arguing with each other. You just let whichever one win. And if you want it, if you're looking to dump as much as possible, you try to skew it so that the diversion load will win. If you don't want that heat, if it's really hot and sunny and you're too hot, you skew it so that the solar controller comes in first and backs off before the diversion takes place. That's it. I hope I didn't overrun too much. If you have a project, get in touch. This is what I do. I'm fascinated by it and I'm quite happy to help. Thank you.
We may have a few questions before passing the floor to Jonathan. Yes. You are raising your hand. Maybe you want to speak. I don't know. I can let you speak if you want. Or just write a message to Q&R or to the chats. Okay, no questions. Jonathan, you can share your screen maybe.
All right.
And then we can have more questions during the panel.
All right.
Sorry, there is a question.
Okay.
Is there a publication of the TriStar follower? A publication, sorry.
Yes. Yes, I have put a page about it on my website. If you go to scorigwind.co.uk and look under charge controllers, you will find there is a web page with a circuit diagram and a little explanation of how the TriStar follower actually works.
I can post that into the Discord group later.
Ah, yeah, great. That would be great. Go on, Jonathan.
All right.
Feel free to.
Thank you. Okay, thanks Hugh for the good presentation to get a good start into charge controllers. I think I will continue a little bit on that topic, but just first I would like to introduce myself. My name is Jonathan and I am from Austria. I started the company Pure Self-Made, which is some sort of small company, but also with some charitable background to basically share a lot of knowledge, and this is basically the main objection. Yeah, and I'm a teacher for hands-on workshops, I could say, in terms of building wind turbines and also designing the whole system, the off-grid system, maybe some grid-connected stuff as well. And I do enjoy building new hardware for small wind, playing with new project ideas, and charge controllers and so on, everything that is involved. And currently, for example, I'm working on a new plan for basically some new small book that contains all the ferrite turbine designs in one book. Been working on that a little bit with Hugh as well, but that's not related to charge controllers, just to show what else I'm doing. Yeah, so there is my email address, by the way, down there, jonathan@pureselfmade.com. If anybody wants to reach out to me, I'm always happy to help and discuss and collaborate. So let's get this started. Basically, some stuff related to charge controllers that I've been doing in the past. There was the Venus charge controller, which was a project that I've been involved with my friends from Wind Mobile, Luxembourg, the guys that make these nice cups here. And they worked with me on this. It was a digital charge controller that we made, basically copying all the parameters from the TriStar controller and trying to replace it in some sort of self-made circuit board. And that worked really well. We put also a data logger into that circuit board, so it records data of all the things that the charge controller experiences, like all the currents and voltages that happen. And we had it working in the field for 2 years. It's still working. It's fine, although it's just a prototype and there's a lot of stuff to improve. And I would probably not stick to that design if I do it again. But it was just a collaborative project with my friends from Wind Mobile, just to do something and see how it works. So that was one experience I had. And back in the days, I also built some simple analog charge controller circuits, just not exactly the same, but similar to the things that Hugh has just shown in his presentation. It's just some simple comparator of voltage, and that will switch on a load above a certain threshold and switch it off once the voltage drops. So it's kind of very crude and for small systems, but it worked, and it's also not too bad if you want to keep it really simple. Just some things. And of course, I've been working with a lot of other things like the TriStar controller and the commercial products that you can get. And today I would like to dive into one thing that is just happened this year. It's an interesting project in Germany, in the east of Germany. And I would like to talk about the issue that Hugh has just also started to talk about, the multiple charge controllers in the hybrid system, which is something that happens quite often, especially if there is already a system installed when I come somewhere to put a wind turbine. And also if the system grows over time and people start adding more and more stuff to it. So what the thing is in this part here, in this particular project, we had two F wind turbines, both calibrated to kick out about 550 to 600 watts in gusts. They were built over 2 years, like in 2 workshops following, one in 2019, one in 2020. And there is also a 1 kilowatt solar panel, solar array on the roof that has some, considerable power. It's just some old panels that they had lying around, but they're still about 1 kilowatt peak. And we have a 24 volt system there with 260 amp hours about, which is rather small for such a big power coming in. Basically, it should be much bigger in terms of capacity, but it was a matter of budget for these guys. And so they decided to buy some small batteries first and then stock it up later and get some bigger capacity. And so we had these 3 sources. We have 2 turbines. So we have three different sources of energy that will create a little more than 2 kilowatts in the end. And we have, on the other side, we have these controllers. We have a TriStar for 60 amps. And we have a Victron Smart Solar MPPT controller, which I just bought because of the MPPT function I wanted to use for that solar array to get more of it. And we decided to install the TriStar follower circuit because we wanted to use the energy that is being dumped to heat up some water in the building in a hot water tank, basically. And it was too far away to do that on DC. because it's like a 30-meter wire to that hot water tank. So we had to use some high voltage AC grid level voltage for the dump loads, which yeah, that's why we decided to use that follower circuit that Hugh Piggott has published on his website. So to have a closer look, that is the experimental circuit board of that system. I say that it's experimental because there is no covers on the stuff, and some electricians start crying when I show it to them. But I actually enjoy the fact that I can go there and plug stuff in and connect some measurement devices and whatever, and play around with it. And actually I like it. It's pretty clean to my eyes, at least. And I like experimental stuff. Just to justify this. And yeah, there is the other thing going into that. I don't want to talk about all the wires. It's mostly about the charge control stuff that I would like to explain. What you can see here is that we use this smart solar charge controller, the MPPT, the Victron, the small blue box on the right. And just above that, to the left, the TriStar controller that most people already know. And it's basically just as simple as it gets. It's the Victron controller is in series with the solar panels, basically, before they go onto the DC bus. The DC bus in here is the two copper rails in the center bottom where all the stuff is connected in parallel. So we have this Victron controller that we bought to utilize the MPPT function and get more of the solar panels. Basically, that is in series with the solar, so it doesn't affect the wind stuff that's going on. And then we have the wind turbines coming in through that thick black wire in the center top, going straight to the battery as we normally do. And we have the TriStar controller connected in parallel to the battery, just as you normally do with a TriStar for DC dump loads. On that TriStar, we put 2 kilowatts DC dump loads, just to be sure that it's strong enough and can handle the power from that 2 wind turbines. Basically, it doesn't need to be that big in that case, because it's only a bit more than 1 kilowatt from the wind turbines, but we needed to excuse me, use that too because of the resistance of them. So it's just designed that the DC dump loads on this system can take about like 20-30% more than the wind turbines can deliver. So the dumping is related to the wind turbines. That was the idea first. And the other thing is on the left of that TriStar, you can see the TriStar follower, which is in that small little box. I think on the next slide, you can see on the close up. So basically it's the stuff in the left, not besides that box with the circuit. Right on the right, you can see the Cridom solid state relay that is used on the TriStar follower. So the thing why we use that, as I said, is because we wanted to use some of the power from the inverter to heat up the water in the tank using a AC heater. And what it does basically, I just switch forward. Here's the schematics of the followers. It's just a very simple stuff. Basically, it's just a few resistors, some diodes, some Zener diodes, and 2 capacitors, and the Cridom solid state relay that is on the left, the one that you can see here on the right side. So it's here is the full schematics of that system. It's in German, but it's about it's not that important. Just to look at the schematics. What we can see here, just to explain it a little bit, is that we have a battery bank and a DC bus and everything connected to it. Basically, on the bottom left, you can see the PV MPPT controller as it is wired straight to the DC bus. And there is the other stuff going on the top left with the wind turbines feeding into the DC. And what we would like to look at here is the TriStar with the TriStar follower. So what you can see in the center part is the number 3 is this TriStar 60 amp dump load controller, as it is normally wired to a battery. And to the right of that, you can see the TriStar follower with its sense cable coming off the dump load from the TriStar controller. So the follower basically just has some two cables going onto the DC bus for the voltage that it needs to operate. And then it has this PWM signal taken from the dump loads, basically from the dump output terminal of the TriStar controller. So it takes the PWM signal and turns it into something that is not a PWM signal, but something like a linear voltage that is going up and down, varying with the PWM frequency, basically. And so the voltage will go up the more the duty cycle goes up from the TriStar. And this voltage will vary between, I think, 3 and 10 volts, which is the input range of the solid state relay. And the solid state relay, I think it's 3 volts, it starts to switch, and at 10 volts is fully on. So that way it regulates the power that's going through that AC heater, which is connected through the Cridom solid state relay and on the inverter. So it's basically on, you can see the things, the inverter on the right, number 7 in the diagram, with the fuse box number 8, and has this AC heater connected through that Cridom solid state relay. So it's this kind of arrangement that we used in that system. It's actually not that difficult to build. The follower is just, as you see here, is just a box with a few components. And that's the diagram from Hugh's website. So yeah, that's the whole thing basically. And the idea was that we won't lose all the heat in the shed on our DC dump loads that are sitting in the workshop there, where there's not a lot of heat needed, but we would like to have it in the water tank. So using that, we could get most of the heat into the water tank, and the DC dump loads will still get a little bit hot, because it's basically made in a way that once the TriStar starts to dump DC power, the signal of that PWM is already strong enough to fire the TriStar follower to a much greater extent. So it will actually take most of the power to stabilize the battery voltage through the rectifier through the inverter. So it's the DC power is just a little bit once the follower is on. So it's creating a little heat on that DC dump loads, maybe like 10%, but the rest 90% go into the AC dump loads through that follower and Cridom circuit with the SSR. So that is the idea. It's very basic, and the analog stuff going on, that is just additional. And there are some challenges with that, because it's quite complex in the end. You have a lot of things working with each other, even though the diagram is simple. We have, the thing first is that the follower, well, once it starts switching on, it kind of starts to oscillate, because it will kind of draw all the power through that AC dump load, and then since it has some capacitors in it, it will kind of start to oscillate at a low frequency, and it's not that stable, I think, although it's not a problem, but it's not as stable as a nice clean PWM signal. And that is one thing. I think it's also here on my list of challenges. To go through them quickly, that were some learnings that I could take from that project. So the first thing, also the algorithms of multiple charge controllers don't align properly, because one is a Victron charge controller and the other one is the Morningstar TriStar. So yeah, we can actually make them play nicely alongside by adjusting the voltage settings. And we did that in the end, that we set the PV dump load, PV controller, the Victron one, a little bit higher. So it will not reduce the PV power before the TriStar kicks in. So first thing happens when the battery gets fully charged is the TriStar starting to dump, And since the follower circuit is connected, it will dump all that power into the hot water tank, which is what we want. That is all nice. And even if the TriStar follower goes into any other charging mode like float and bulk, it will also follow that. And so the TriStar follower will take the heat into the hot water. And the other thing is, if the hot water tank gets switched off because it's hot and the thermostat of that heater is switching off, the TriStar follower doesn't take any power from the AC side of the inverter, which means that most or everything that's coming into the system, like the solar and the wind power, going into the DC dump loads of the TriStar controller. And so they will get to 100% duty cycle because they are too small to handle all that large amount of solar coming in. And the voltage would rise a little higher, and then the PV controller, the Victron one, will take some of the solar back off, which is, I think, not ideal because the dump loads don't need to get that hot, so we really should put them to another place. And the other thing that happens...
Jonathan, I don't want to hurry you, but you're a bit late on time.
I'm sorry. Yeah, now coming to an end. So I'll just try to summarize that. So you have this kind of situation that all the power goes into your DC loads, DC dump loads. And that isn't something to look at. You need to make them big and put them somewhere where they don't get too hot. And, you know, as Hugh has said before, the other thing is that, as I said, it starts to oscillate a little bit with the TriStar follower. But I think that is also due to the fact that the batteries are quite small in that specific place. And another thing that might be more important is the complex system that is hard to understand by a customer. So I think I'm the only guy there who knows how to program that specific system. And the guys who live there where I did this workshop, they don't probably understand that fully, and they rely on my help. So it's nothing really easy to handle. And you need to know, and you need to play with that and see how it works. It's not plug and play and everything is fine, but needs some attention paid to that, and improvements over time on the specific system to make it run the way you want. The other thing to improve here, or to do that it works fine, is that you have one controller that is the leader, basically. So you don't actually make them interfere with their charging algorithms by setting one of them on a higher voltage threshold. That can easily be done through some programming interface or something, or on the controller itself. And something I would prefer is to have more control over the whole system with the AC dumping and the DC dumping, and how that works alongside. And I thought that it might be cool to have some Arduino-based controller solution that handles both the AC and the DC dumping, and is programmable so you can actually tell it what to do, and not just dump based on some voltage algorithms, but also tell it what exactly to do, and so it doesn't oscillate by stealing one signal from another controller, and make it do something that is maybe not intended to, although it works fine. But I would like the challenge to create some Arduino-based system that you can actually program a bit more, so you have more control on your whole off-grid system in that case. And that is something I would like maybe some other people to talk about, what they think, and how that could be implemented into some charge controllers that are already on the make, that some people are building here in the network. I'm talking about the AC dumping feature, that you can trigger some solid state relay that dumps power off your inverter instead of the battery directly. So that would be one thing to maybe collaborate, share some experience, and I'm more than happy to do that. And so reach out to me on the Discord or via email, and on my email address that's on the bottom here. I hope I didn't take too much time now, but it's a thing that's quite complicated and a lot of stuff in that specific project. I could still talk more about it. I don't want to go too hard on it right now. And that would be my presentation so far.
Thank you, Jonathan. It was really interesting. Like both your presentation, Hugh, and you, Jonathan, are really compatible and explaining in depth with theory and then practice just after. So it's really interesting. Do you have questions, guys? In the meanwhile, maybe you can try to share your screen, Fernando. And if you have like an introduction to do, or maybe Fernando, what you want to do is do your introduction in Spanish and Manuel will translate. Is that it?
Buenas tardes a todos. Antes que nada, quiero agradecerles el espacio que nos brindan para poder contarles lo que estamos haciendo desde el colegio. Mi nombre es Fernando Cembalo. Manuel, ¿vos me escuchás?
Yeah. Good afternoon to all of you and good night. I want to thank you for the time and also, tell you that I am Fernando Cembalo from Argentina, from the south of Argentina.
Mi trabajo es coordinador de proyectos, soy profesor de electricidad y de energías renovables. Lamentablemente y por suerte no podemos contar con Sergio, que es nuestro profesor de electrónica, porque fue padre ayer. Y bueno, la idea nuestra era presentarles a ustedes un regulador de carga que desarrollamos en el colegio, lo armamos y que nos está dando muy buen resultado. Manuel.
Well, I work as a professor and also as a project manager on renewable projects. And the idea was to tell you about one of our projects that included a controller, a different controller from the advanced ones. So that we developed the last years with Sergio, another professional of the institute that has been recently a father, so he was complicated to participate today.
So I will share the video. Where is it? Yeah. Do you see the audio? Oh, no, it will be maybe hard to share the audio. I hope you will get the sound as well. Tell me if you get the sound.
My name is Sergio Ruppel. I work for
Does it
Right.
work?
Yeah.
Don Bosco. I'm a teacher in electricity, and I'm one of the developers of the charge controller solution we are using in the systems we develop. Well, we all know the difficulties in these systems. We need to control the charging voltage to our batteries. We in particular developed this system with our students, and we think that they must understand everything that it's done, so it's more useful to them in the end. Our solution must be something that they can understand and replicate. Our main idea is to keep using the dump resistor in order to load the generator. We know that that the lead acid batteries are getting a high voltage, around 3 volts per cell. It will get damaged, and eventually over time they can be destroyed. So our main idea is to use this dump resistor to load the generator and keep it in a working range, so it won't damage the batteries, converting this energy into heat and lowering down the aero speed. Our generator can provide around 350 watts on 24 volts. This is the size we are making. That's roughly around 15 amps. We have very high winds on this location, so even when the mechanical design of the Piggott allows the generator itself to turn down to a safe position, twisting itself, in this area we've seen it close down and hit with the blades, the tail of itself damaging, or the blades or the tail of the aero. We need something simple and cost effective, because if it's not simple and it's not cost effective, we just buy some Chinese solution and use that instead. We have two ideas for the design. One, which is something like a copy of what wind empowerment is already doing, with a PWM controller like the TL494 or the SG3525. And this will just work fine, so we have a starting point there. And we thought that we could use a microcontroller, which in the future will allow us to do more things. So we went for both designs. We made one with the SG3525 as it's already working, so we start there. We know how it should work. We have a schematic, so we make it a copy of it with a single board PCB, single sideboard PCB, I'm sorry. It's very reliable and cheap. It's very easy to understand how it works, and it does not offer much control, besides the fixing voltage setting that it has, and in the ability to choose if the system will be using 12 volts or 25 volts, 24 volt systems. So we have a starting point there, but we weren't satisfied. We wanted a bit more. The design is quite simple, and the schematic is widely available on the internet from the wind empowerment page. It has this the center AC, which is the PWM controller, some MOSFETs on the right, and some voltage and the voltage control on the left with the power source. The BU 408, it's the one we are using here because it's available. We have a single board, and the only thing we change from the board that wind empowerment uses is that we have the MOSFETs on one board, but the IC, the SG3525, it's on another board that can be stacked on. So if the MOSFETs get damaged, and if the PWM controller keep working, it can just replace the power board and it will keep working, making a simpler solution to fix. Our design, the other one with the microcontroller on it, works with an Atmega on an Atmega 85 based design. It's an Atmega microcontroller. It uses a totem pole driver because the Atmega cannot drive the MOSFETs by itself. It works by measuring the voltage, the battery voltage through a resistor divider, and then control the PWM output. For us, it's a pilot test. If it results in a reliable system, something that we can trust for a long period of time, we can make an improved version of it. And we thought that two ways of improving the system. The first will be that allowing a buck boost stage, something like a CPIC converter, so it can be more versatile and work with solar and eolic generators. For mixed systems here in the Patagonia, we can use both systems. We have plenty of resources. And another improvement will be to load into the Atmega most voltage steps, so we can use batteries with different conditions. Some batteries may be a bit dry off or with a lower battery voltage. So the system will be able to read those voltages, and understand things that it must get, for example, a higher current at first until it reaches a certain voltage, keep that voltage for some time, and then slow down a bit to keep it on a float voltage, for example. 2 or 3 stages at least could be embedded into the design without very much effort. Of course, the PWM solution is working with the fast PWM solution. Only the PWM solution in the system doesn't work quite well because it has a very low frequency. The main part of our system is obviously the power stage, which is quite simple. Simple totem pole and drivers made with the 2N3904 or 06, the NPN and PNP pairs, complementary pairs, and MOSFETs. We choose the IRF 840 because they are quite cheap here in Argentina, and we can find it almost anywhere. It doesn't have much more. The resistor divider is just that. Well, with our improvements, we thought in this idea, the CP converter or the buck boost stage, and allowing the more stages on the charge to be able to use our system in battery recovery systems or as a battery recovery. We also thought that to keep the system being more versatile, we should include the rectifier bridge on this board, and also we can include a small inverter, something that can be used to power some light or small equipment in the shed where the system is being used, without the need to buy an extra inverter, which they tend to be quite costly. Also, our rectifier bridge right now is using silicon diodes, but we know they have around 1 volt of voltage drop on each diode, and with 15 amps it can get a lot of heat. We have a lot of energy that it's not being used, so to be able to make something more efficient, we can use a MOSFET or an SCR rectifier bridge. This will be also an improvement as something more like a professional level system. So far we have a lot of designs made in small boards. We're testing the small pieces of it. This is or very little mess. This is the inverter right now. It lacks of the control board and the boost converter board, but they are quite simple. The boost converter board is a TL494 driver. For a push-pull converter, we are using some small ferrite cores from ATX power supplies. We can find them very cheaply. It's AI30, around 100 watts. And for the controller board of the H-bridge for the inverter, we keep using an Arduino Uno, which is an Atmel 328P. Quite simple, easy to program. We have this board already working. It's a testing board, but we can easily add a charge controller on the left side of it and have a very versatile system, cost efficient and effective. Well, thank you very much for listening to all of this. I'm very sorry for the caveman-like English. It's the best I can do right now. And if you have any questions or want to ask anything about this, that's my email, and you can write me anytime. Thank you very much.
So that was Sergio's presentation. Fernando, maybe you want to conclude?
Fer, quizás quieras decir una conclusión.
No, a ver, yo soy eléctrico y no electrónico, por eso preferí que hable Sergio. Nuestra idea fue crear, o bien no tanto crear, sino realizar un regulador de carga económico, robusto y como nosotros trabajamos mucho en los pueblos originarios y pobladores rurales de la Patagonia, tiene que ser algo confiable para que no tengamos inconvenientes al momento de, por ejemplo, de tener que hacer alguna reparación en el funcionamiento del mismo, ¿no? Nuestra idea es seguir desarrollándolo, por eso estamos abiertos a cualquier idea que nos pueda ayudar. Y también queremos modificarlo y avanzar para armar reguladores solares que necesitamos. Y en este proyecto que estamos comenzando de realizar turbinas hidráulicas, entonces queremos también ir mejorando este regulador, adaptándolo, y con un Arduino poder también controlar algunos valores que creemos que son fundamentales para tener un balance al momento de ver el funcionamiento del sistema, ¿no? Y especialmente del regulador. No sé si fue muy larga la frase, Manu.
Let me try. The main idea is to develop a specific device that is cheap, also robust, and also reliable. That are the three main objectives or goals. So we are testing it by now. We want to improve it. So also we want to try it with the solar systems and hydraulic systems. So we are open to know more for these devices, and open to be in contact with you for improving it.
Well, thank you.
Bueno, muchas gracias.
Thank you for this presentation, and I hope that everything is fine for Sergio and his new family. Maybe we will take some questions after the end of the panel, and I propose to give the floor of speech to Adrien for the last presentation of the panel. Adrien, the floor is yours. Be careful, you are muted.
I think it's okay now.
Yeah.
Okay, hi everyone. So I'm Adrien. I'm going to talk about OSWACC project, Open Small Wind Analog Charge Controller. So that is the charge controller that has been mentioned as the wind empowerment charge controller. So I presented myself yesterday a little bit, but so that project was part of my engineering courses at INSA Lyon in France. And I presented the WE India 2018 Wind Empowerment Conference 2 years ago. And I will present a little bit the functioning of the controller, the objectives of the project, but also important feedback from field testing. So a little bit of history of the project. In 2015, Bastien Gary made a V1 in Tripalium Association, which is like the French network of locally manufactured small wind turbines. In 2016, a friend of mine, Clément, improved and made the second version of the controller, but it was not reliable enough, it was not robust enough. So I improved it in 2018. I mostly improved the power circuit and did a thorough calculation of the heatsink to be over dimensioned, so it doesn't burn the MOSFETs, which was the main problem on the V2. And also I added some precision and temperature compensation and documentation. And I proposed in this year to INSA students, an engineering school in France, to do a V3.2 to ameliorate the board. Okay, we have seen this with Hugh, but I just wanted to emphasize on the fact that the battery is a really sensitive element in the power chain, and it has to be taken carefully, charged carefully. So in small wind, the bulk phase is when it's not regulated, as Hugh said. And when the charge controller is on, it's trying to maintain the topping voltage. So our goal is to actually be able to calibrate the controller so it maintains really precisely this voltage, not to overcharge or to undercharge the battery. How to shorten battery life? If we constantly undercharge or leave the battery uncharged, there is some oxidization on the battery and corrosion, which can shorten dramatically the battery life. Extreme temperatures, if they are not taken into account by the charge controller, are very problematic, because as temperature is a catalyst, the battery does not behave the same in hot temperature or in cold temperature. Not equalizing the battery, so for open lead acid batteries, which means like not periodically boiling the battery, would result in more and more corrosion on the plate. And overcharging, especially for GL or AGM or VRLA batteries, which cannot like boil, can be like a permanent damage. So we have to compose with all this. And one main modification that I did on this controller is to compensate the topic voltage in function of the temperature. So a battery with a high temperature behaves like its behavior is everything happens, the chemistry inside happens faster. So it's overcharging. With the same topping voltage, it's overcharging. And if we apply the same topping voltage on the low temperature battery, the battery is undercharging, because all the chemistry inside is happening really slow. So here is a graph on which is represented battery temperature on the x-axis, and on the y-axis absorption voltage. You can see that on the range of 40 degrees Celsius, there is a difference of actually 2 volts in the topping voltage, battery topping voltage. So it's critical. The classical compensating for lead acid battery is 24 millivolts per degree per 12 volt cells, which means 48 millivolts for a 24 volt battery. And so another point that I took from Victron documentation is that battery lifetime can be reduced up to per 2 each 10 degree average temperature increase. So if the average temperature of the system is 10 degrees above the recommended average temperature, it can like decrease dramatically the lifetime of the battery. So how does it work? I think we have seen that. The controller is based on the second model, the second type of controller that Hugh presented in his talk. It's just about diverting part of the current in dump load with a PWM. So the charge controller is basically a power switch that is switched on and off with the pulse width modulation for enabling the battery to continue to charge a little bit, but not to overcharge it. The extra power is diverted to a dump load. I would pass on that because we don't have a lot of time. So the design requirements were given by Thiol in France, that made the presentation yesterday, and said to me, okay, I would install this controller on 12 volt, 24 volt, and 48 volts wind turbines with these characteristics. So the maximum amps that it would have to support would be like 35 amps. Yeah. So that were the criteria of design. So the design, this is the, actually it's, the goal of the project was to be also an educational way to train students about how to build electronics and to understand how it functions. And so that was very interesting to do an educational material to lead to the charge controller here. So the max amp rating is 45 amps. It's possible, like with the same board, to use the board for 12 volt, 24 volt, or 48 volt systems. It has a power MOSFET here. It has a heatsink. The goal was for the project was robustness first and easy to troubleshoot. So fully analog and easy to assemble through hole. So like using very generic components that can be found everywhere around the world, and low cost. So here the cost is about 35 euros, but actually it's because of the high cost of the heatsink and of the 3D case. But I think it could be further down. A little bit of the results about the charge controller. So this is actually measured behavior of the charge controller with temperature. So we can see that it compensates very well. It is on a 24 volt system, and we can see it compensates by 49.6 millivolts per degree. So which is like with a 3% error compared to the Victron recommendations. I did a little bit of testing with the temperature, and I could see that it was stable. I tried to burn the MOSFETs with a 48 volt generator and going full blast on a test rig for 1 hour, and I almost burned the generator because that's what dumping 100% on the dump load. So I couldn't manage to burn it and was stable in temperature. Couple more results. So these results have been measured by the Guillermo and 500 RPM friends, and they shown that the controller was actually dumping and maintaining a good constant topping voltage. Actually, I would be really interested into seeing how it evolves with the temperature, battery temperature, because I have designed so it compensates. And so if you could provide me the raw data, I would be really keen on to see if this behaves well in the time. But this is yeah. And
thank you, Adrien.
Yeah, I think I just wanted to go 1 minute on the open source hardware deployment. It's not too late.
Mm-hmm. Go ahead.
I think there are some main obstacles that I could see, which are getting the PCB board. These nice PCB boards are made in China, but actually when you are in a remote area and you just have the ink transfer method, how can you like build a 2-ounce copper PCB board with 2 sides if you don't have enough material? So one of the, I think the issue is getting the PCB board, and maybe designing a 1-side thick copper PCB board with maybe a few wires under would be a good solution to enable the hardware deployment and building easy around the world. Bill of material, is sometimes some components are not available in the country. Reliability, actually, on the one hand, it's hard for developers to have their hardware field tested with reliable and useful feedback data. We are lucky to have the Argentinian data for this controller. But on the other hand, it's hard for wind pilots, as we call it in France, wind turbine owners or practitioners, to trust open source hardware that is still in development, which is the case with this project. And of course, I understand them, they want to burn off their batteries. So yeah, I think one connection to make is actually connect with the measurement group to be able to have test sites around the world and to ship the open source hardware to have some feedback on the design behavior. I think that's all for me. And if you want to contribute to the project, it's possible. It's on GitLab, and yeah.
It's also highlighted on the Wind Empowerment website, so you can access the wiki of Adrien's project through Wind Empowerment, through the technology working as well.
Yeah.
Thank you for this presentation, Adrien. I would like to raise a question from Peter to all the panelists, which was, do you guys have experience with lithium-ion batteries? Or lithium in general? Could be LiPo as well. Lifer, Lifeu. I don't know how to pronounce this in English.
I do.
You have an experience with it?
Yeah, well, I have lithium batteries in my home. What I'd recommend with the lithium-ion batteries is usually the LFP type, the lithium iron phosphate, is to get a manufacturer who has some sort of integrated solution with the electronic side of things, the charge controllers and the inverters and so on. And then you have a relatively trouble-free experience. The battery has an internal battery management unit, and that's going to want to communicate by CAN bus or some such protocol with the charge controller to tell it when to stop charging, or with the inverter to tell it when to stop using power, because the battery is quite vulnerable to being overcharged or over discharged. Everything seems to be very reliant on software. So in my case, I've got a system where the battery manufacturer, BYD, has a relationship with Victron so that it can talk to Victron, and my system is Victron, and that's all fine up to a point. Trouble is, Victron don't have a diversion load controller, they don't have a wind turbine controller, they only have solar controller and inverter. So I've got a little bit of a problem with my wind turbines being confident that they're not going to damage the battery, because they're just going straight into the battery. What I have put in place is a very good diversion control system to make sure that the battery never reaches 100%. So it's not necessary to intervene and limit the charge rate, which is what would happen normally with the solar system. The battery would tell the solar controller to stop charging. Well, I don't get to that point because I divert in the 90% to 96% range and make sure it doesn't get up to 100%. But at the same time, the battery does have some contacts, relay contacts called allow to charge. And if it doesn't allow to charge, then I have a brake relay that shorts both wind turbines, basically stops them. So I have a reasonably good confidence with the combination of those two protections, good diversion charge control, and also the brake relay working off the allow to charge contact on the battery management unit. But I'm still not 100% sure that this is going to work in the event that there were an error with the battery management unit. If it went into an error state, whether that would shut the battery down without shutting down the wind turbine, that's a little bit of a worry. So my system gets more complicated still. I have also got a lead acid battery working in parallel that is charged through a separate rectifier, so that in the event that my lithium battery were to pull the plug and disconnect, my wind turbine is still connected to a lead acid battery. So like I've got these 3 different safeguards. It's really complicated. I'm hoping it'll get simpler in the future. My understanding is growing all the time, but it's not enough that I can really say this is how you should do it and it's easy. As I say, this is what I've done and it's working well, but it's really complicated.
What about the charging states? Would it be the same with lithium battery as with lead acid batteries?
No. Well, sometimes they will specify a voltage for the absorbed voltage and for the float voltage, but well, with my battery, from my experience, I would say that you could just go up to a certain voltage and then you could say it's full. It turns a corner, the voltage will be around 53 and then it just goes up, 56. So if you catch it at 54.5 volts, you can catch it there before it goes to 100% and cuts off. You could bring in your dump load at that point, but it behaves very differently from a lead acid battery. It doesn't really need to be kept at a particular voltage. It's more like the voltage suddenly rises when you get to 100%, and that's the most reliable way to know that it's reached 100%. You'll be probably trying to fly by a amp-hour meter that's showing state of charge in percentage terms. Most of the time the battery voltage is pretty steady around 52, 53, so you don't really know, other than by the state of charge amp-hour meter, you don't really know where you are. But that gets out of calibration after a while. You go up, you go down, you go up, you go down, and after a while it's 10%, 20% out of calibration. So it's not until you get up to that point where the voltage does a hook upwards, and then you can tell it's definitely reaching 100% now. You can recalibrate, you can bring in your dump loads. It's complicated. It's a different experience from lead acid batteries. And as I say, I haven't got the simple answer for you, but it's yeah, I'm gaining an experience, and this is what I've been doing.
Thanks.
And so Peter is asking if you recommend it because of its high investment compared to lead.
Yeah, I bought it because I wanted to learn. I'm not unhappy. I've spent a lot of money and I've got quite a small battery, but it's very, very efficient. Compared to my flooded lead acid battery, it's 100% efficient, really. It gives me back what I put into it. The lead acid battery, as it gets old, it gets warm, it uses energy. You're using hundreds of watts just keeping the thing ticking over in float charge. And then it's time to scrap it and get another one. The lithium battery, I think it's going to have a longer life. It's going to give me much more of my wind energy back as useful energy in discharge. Like I mentioned, I do have an auxiliary lead acid battery that I can use not only as, if you like, an emergency place to put the wind power if the lithium pulls out, but also as a backup. So I have a relatively small lithium battery. It works fine most of the time, but if it's running low and I don't want to start the generator, I can keep going overnight on my lead acid battery, and that's quite a comfort. But again, I don't think this would be a system for everybody. It's really complicated. It's possible to use a combination of lithium lead acid to get a cost-effective solution with good capacity and good efficiency. But it's like Jonathan says, perhaps the biggest problem sometimes is putting together something the customer can understand or the user can understand, so that you don't have to be sitting there explaining every time something happens.
Thank you for this experience.
You're welcome.
I'm afraid we will lack some time to have a proper chat after the panel. Unfortunately, you guys took a bit longer than the expected time slots. So I propose, unfortunately, to jump to the second panel, which is dedicated to power electronics. And I believe it will be complementary with the discussions that we were having right now, because The first panelist is Martin Jäger, and he's working on open hardware solutions for MPPT, for PV mostly. But it's directly linked with the discussions that we were having on the possibility of having charge controllers that were having some SMPS functionalities. So I hope we will have a smooth transition between the two panels. Martin, I guess the floor is yours. You were muted.
Here we go.
Yeah.
Now you also see the screen properly, I hope.
Everything is fine. We do see the controls up there, but it's fine. It's not
go away.
Too annoying.
1 second, I'll try once more. Get it. Yeah, it's annoying.
Well, it's okay-ish, let's say. I think we...
Yeah, but then we can't see the headers anymore. Ah, okay, here we can take it somewhere else. Let's see if we can take it out.
Yeah, but now you're muted. Let me unmute you. Yes, it's okay. I unmuted you.
Thanks. Okay, yeah, I'm Martin Jäger from Hamburg, and I want to introduce a bit of the work that we're doing in the LibreSolar project. We're a group of a few people yeah, here in Hamburg, and also some contributors from all over the world, because it's an open source project, but still quite small. And yeah, as the name suggests, it's mainly about solar, but we are also trying to work together with some people from the Erni kollektiv to integrate our charge controllers with wind turbines. And so I'm happy to talk a little bit more about that here in this session. First of all, a very small introduction why we think that open source is so important for tech products in general. So if you look at other products like food or clothes, then consumers usually have a choice whether they want to use conventional products or they want to buy organic food, for example, or fair trade clothes. And those are both yeah, labels or processes and ideas to protect the humans and the environment. But for tech products, you often don't have this choice. And we think, or I think, that open source would be a very essential aspect of any product to improve on this situation. Because only through open source, it's possible to share things and then let other people participate in the knowledge, in the global knowledge. And also open source allows to make designs more repairable, and if lots of people contribute and improve the design, they will also get more solid in the end and break later. And if we put everything together, then only open source also allows to manufacture a distributed way, which is still very difficult for electronics at the moment, because all the chips are usually produced in very centralized factories and then shipped all over the world. But if we start at least with repairable designs and things that can potentially be built on your own, then we're stepping into the right direction, I think. So saying this, yeah, what is our project about? We're trying to build building or develop building blocks for renewable energy systems. And yeah, we started off with some solar systems. And if you have a solar panel and a battery, you of course need a charge controller. And this is basically a DC-DC converter if it's an MPPT charge controller. And yeah, we just talked a little bit about battery management systems. So if you have a lead acid battery, then this is already the most basic system you can have. But if you have a lithium ion battery, then you need a battery management system that takes care of the single cell voltages and so on, and makes sure that the battery is not overcharged, because in this case, it would maybe lead to catastrophic events like thermal runaways, instead of just damaging your battery. So yeah, we also started developing an open source battery management system, which is currently available in different stages. And yeah, one is for very small batteries, and it goes up to 15 cells, which is almost typical 48-volt batteries if you use lithium iron phosphate cells. Then, yeah, those charge controllers, I will go into a bit more detail later, usually also contain a load switch, which makes sure that the battery is not deep discharged. And yeah, as it is fully programmable yourself, you can also use the integrated DC-DC converter to convert between batteries of different voltages. So it makes it possible to integrate other batteries, like a bicycle battery, which runs at 36 volts nominal, with a system that has a 12-volt or 24-volt battery. So that's everything what we've done or tried so far, with the charge controller probably being the most robust solution at the moment. And what is missing is the integration of wind systems. That's why I'm here to yeah, evaluate with you how we can collaborate. And also in the very quite far future, maybe, to develop an open source hardware inverter which can interface with AC grids. And I think this should actually be bidirectional, so that it could be used as a grid-tied inverter, but also supply power to the DC system from the grid, so that you don't need redundant cabling for lots of your consumers. Okay, yeah, the overall system is mainly meant for 12 to 48 volts, with the charge controllers currently only supporting 12 and 24 volts. So if the system is run at 48 volts, the maximum power is around 2 kilowatts, so quite small scale. Yeah, also compared to wind turbines, which usually seem to have a bit more power than small solar home systems. And yeah, we also try to incorporate many different possibilities for communication and monitoring. And so far we've been working with LoRa and LoRaWAN, and with Wi-Fi, with CAN bus, and GSM communication as well. Yeah, so as told, this is more a project for yeah, also for learning, and just because it makes fun to build stuff yourself. But we are also working on some project in the energy access sector with partners from the UK, and we've built up some solar home systems built on the LibreSolar charge controllers in India. And currently we are doing a project in Rwanda, which is quite interesting, where we want to build up a 48-volt DC grid, which interconnects different homes. And if one household has excess energy, it can share the energy to the neighbors via this 48-volt grid. And such a grid approach makes most sense if the system is heterogeneous, because if everyone has a solar panel, then all the batteries will be full at the same time, and then you have nothing to share. But if we had some more wind turbines and other energy sources, maybe hydro even, in the system, that would help to make the overall system more reliable. Now, yeah, we'll give you a quick overview of the charge controllers that we've developed so far. So this is one of the rather small ones. It's an MPPT charge controller, which you can see with the inductor. And this one is only 10 amps. And so it's more meant for solar home system type of applications. And yeah, the components it has is, of course, it has some power terminals where you connect the solar panel, the battery, and the load. And then, so that's also something you can buy off the shelf. But the interesting part about the open source approach is now that you have an extension connector. This one is called the UX connector. It's from a project from Olimex, which is a company that sells lots of single board computers and other stuff, all in open source hardware. And they specified this connector for modular approach for extension modules, mainly for different communication stuff and for displays, for example. And we use this connector to use the same base board for the charge controller, and then connect, for example, LoRa or GSM SIM 800 module for solar home systems with monitoring, remote monitoring, and pay-as-you-go functionality. Then the microcontroller we are using is from STM32 family. So they are quite powerful usually, even though they are often at the lower end of those microcontrollers, but a bit more powerful than the typical Arduino controllers. And we're currently running the Zephyr real-time operating system on it, which is maintained by the Linux Foundation. And it's quite a cool project. They have a very good code base, very high quality code. And one of the very good things is that it has lots of even industrial grade solutions out of the box. So it has can open a stack, all the internet connectivity features, and Modbus TCP, for example. So in theory, you could quite easily integrate the charge controller via this additional connector with other existing proprietary systems. The PCBs are all made with KiCad, which is of course important if you want to do open source hardware, that you also use open source tools. And then all the devices usually contain an external communication port, which is a serial interface in this case, or CAN bus for the slightly higher power versions of the charge controllers. And now we're currently developing a more powerful version, which is called the MPPT 2420HC. The 24 stands for maximum battery voltage of 24 volts. The 20 is the inductor current, so the low side or battery charging current. And the HC stands for high side load switch, which is this one. And CAN C is for CAN communication. And this device is built on a quite powerful STM32G4 microcontroller, which has some nice integrated analog features, and it also runs at quite a high speed so that you can implement more sophisticated digital control algorithms in it. And the basic layout is for this charge controller, which is originally meant for solar applications. It's this DC-DC synchronous buck converter power stage. Then we have a current measurement here at the inductor, and we have a load current measurement and the load output switch, and an integrated fuse, which acts as a reverse polarity protection and also as an overcurrent protection of last resort, because originally the overcurrent should be detected already by the load output and it should switch off. And then we have one additional MOSFET, which is normally not needed for DC-DC converter, which is this one. It is the reverse polarity, the reverse current flow protection for solar panels, so that during the night no current can go from the battery into the solar panel. And this is not really needed for wind application, but it's also not harmful because it also provides reverse polarity protection at the input. Now, if we want to connect a wind turbine, I think one approach would be to use a standard rectifier, diode rectifier, and then directly connect the wind turbine to the charge controller. But as mentioned already before, we need some additional features to get rid of the input power if the battery is full. And I think in this application, it does not make sense to do this on the battery side, because we are quite limited in the power that we can transfer here. And if we had really lots of wind and the batteries were completely full, we have to transfer all the worst case power coming in through the charge controller and then dump it on the right side. So it would make more sense to install a dump load on the input side, which is shown here. And as said, we are mainly working with solar applications so far. We've got some open questions, which we could maybe discuss later in the final discussion round. So one is if the 80 volts maximum voltage at the moment, so we are using 100 volts MOSFETs, but we only want to use them up to 80 volts, is sufficient for some sensible applications with small wind turbines. Then how should we control the load, the dump load switch? So should should we have a dedicated device that runs in parallel and also provides an additional safety feature if the charge controller doesn't work properly anymore? Or should it be controlled by the charge controller because we have these extension features, so it could be done. And one other very important question, I think, is how we implement the MPPT charging control algorithms. Because with this controller, with the DC converter, we have the possibility to change the input voltage and then get the maximum power out of the wind turbine. But in solar, you usually can connect any solar panel and it finds the MPPT automatically. But with wind turbines, as far as I understood, it might make sense to program the charge controller with a curve that was measured on the test bench to get the right output from the wind turbine. Okay, that's basically it. So here's some links to the project websites. We also have a small community forum, which is not very active yet, but yeah, might get better in the future. Then we had a collaboration project with one of the universities in Hamburg, which is called OwnTech, and we're still working on that, but there are lots of chapters already finished. So we want to provide an open educational resource that goes from system layout via development up until production of components for DC energy systems. Yeah, and all the source code of the hardware, the firmware, and also the sources of the websites can be found on GitHub. Thanks.
Thanks, Martin, for this presentation. There is a question from Nasos who asks you if you can elaborate a bit on the multi-home system.
You mean the 48-volt DC system in Rwanda, I guess? Or, yeah,
I think so, yeah.
Yeah, okay. Yeah, so the idea here is that there are quite a few companies already that provide solar home systems to people, but after a while, those solar home systems are either not maintained anymore and sometimes break. And then you have still some batteries left and maybe some solar panels, but the whole thing doesn't work anymore. So we try to integrate those still existing components back into a grid so that, for example, if you don't have a battery, you just use your still existing solar panel. And then you get rid of those stranded assets and make use of them anymore again. And also for people who have productive use, so for example, shops or people with milling machines who mainly use those during the days, they can have a slightly larger battery, and but they don't necessarily need them during the night. So we could use this battery and they can share the energy produced and stored into that battery during the day. If they stop working at, I don't know, 6 o'clock, then the batteries the layouts should be such that it is then full. And then the energy can be provided to all the other people in the grid, and maybe we can also get rid of some batteries because they can get power directly from the grid, and batteries are always, they fail quite early and difficult to maintain. And so it would be better to have more centralized storage and then share it.
Well, thank you for this overview on your technology. There is a question from Hugh. Hugh, I think you can ask it live.
I'm just curious because systems where people can share power, can have access to another person's battery, could be difficult from a social and commercial perspective. Obviously, if you have a limited resource and your neighbor is using a lot more and is watching the football when the battery's flat, what are the implications in terms of managing the power, in terms of metering, in terms of control, when there might be a perception that it's being abused unfairly by other people on the network?
Yeah, so first of all, the people would also pay for it. So that's currently at least the idea, that the grid would be owned by the community, but they pay to the community. And so if you consume a lot more than others, then you would probably also have to pay more. And the idea is for those very small systems, for the solar home systems, that you set a limit that they would not provide power to the grid if they reach a certain low state of charge. Then they would just stop sharing. And then if no one is sharing its electricity anymore, then you would also, yeah, you can't get anything from the grid anymore. Of course, if you have people who don't have a battery at all anymore, then you have to prioritize, and this needs higher level communication. So that's also partly still to be sorted out. But if you have those people with productive use appliances that only need energy during the day and most others need energy during the night, then there's not that much of a conflict, because then the battery can be used during the night.
Thank you.
You're welcome. Okay.
There is a question from Emmanuel. Any practical experience in the panel with MPPT versus power curve regulation of small wind turbine?
No, not yet. So so we haven't tried out ourselves yet with the wind turbine attached to the charge controller. But so the DC-DC converter is freely programmable. And so I think there should not be an issue, other than maybe the power of the wind turbine is too much for the charge controller or things like that. But in theory, it must be possible to control it such that it's optimal.
Yeah, maybe with a lookup table at first should be fine, I think. Yeah, it's a thing to try, I think.
Yeah, it's also difficult to try, because you can go and buy a solar panel for 100 euros everywhere and try it out. But for a wind turbine, I'm living in the middle of Hamburg, so there's no one with a wind turbine close by.
You should definitely have a trip to Erni kollektiv at some point with Manuel. Yes, he would be pleased to welcome you.
Yeah, thanks.
Okay, I propose that we go on with Adrien's presentation on active rectification, which is another way of implementing MPPT for small wind turbines. And actually, it's a bit the idea that Sergio was proposing at the end of his presentation, by replacing the diodes that consumes a lot of powers and that have a lot of problems by something a bit more efficient. Adrien?
Yep.
The floor is yours.
Super. So I think we have very complementary things in this panel, and it's great to have all the questions of Martin about the power curves and stuff, because I will try to display a little bit information about that to my comprehension. I'm doing a collaborative work at Ampere Laboratory in France with Romain Delpoux, an associate professor that is expert in motor control. So we are trying to move the knowledge from motor control to generator control. So in this presentation, I will present a little bit about passive rectifying, its advantages and drawbacks, and why it could lead to undertake some active rectifying. But before that, we'll take a little bit information on small wind turbine control basic concepts, and then I will go on my first results with active rectifying. So basically, rectifying is going from AC to DC. It uses diodes that are passive interrupters that behave on their own. So overall, the efficiency depends on the amount of current that is passing through the diodes, because they have some conduction losses. So DC bus has a fixed voltage if it's connected directly to a battery. So the advantages of this architecture is that it's very simple, it's reliable, and it's cost effective. But the drawbacks is that when you switch on and on smooth sine waves, then it creates some current harmonics, and that generates acoustic noise. That could be solved actually with a filter, and Latufis and colleagues in the National Technical University of Athens have solved it. But also there is a non-optimal power factor. So which means that in the generator, the efficiency, the current and the voltage are not perfectly in phase, and there are some harmonics. So the overall power quality is not very good. And in these switches, there are some conduction and commutation overlap losses. So basically the forward bias of the diodes, which are actually 0.5 to 0.7 volts times 2, because each time the current takes a path, it takes 2 diodes. So which means that when there are 10 amps passing through 2 diodes, it's 12 watts that are dissipated. So imagine with 40 amps. So AC/DC fixed input output is also a drawback. If you don't have any DC/DC converter in between, so what proposed Martin just before, you have a fixed input output between the actual DC bus and the AC voltage. And this is a drawback because it does not allow us to control the turbine and to control the mechanical operating point that is optimal for the turbine. Because in the wind turbine, there is an optimal tip speed ratio, which corresponds to the design of the blades. And so as the wind speed moves, the wind turbine speed, rotational speed, should be adapted to get the maximum power. So if we go on a little bit with passive rectifying and control and the link with power curves, here are some power curves corresponding to wind speed. So we have 3 meters per second wind speed power curve for the wind turbine. This is 5 meters, etc. So if you connect directly to the battery at the output of the diode rectifier, it's like you fix the speed of the turbine, and you have fixed operating points that correspond to the intersection between the rotational speed here that is fixed and the power curves. So at 3 meters per second, your turbine can operate at this much power. At 5 meters per second of wind, your turbine can operate at this much power, and so on. You could design another generator to match higher wind speed by doing less turns in the coil, but it won't allow you to match the perfect, the maximum power curve. In reality, generator with high resistance in stator and lines, transmission lines, actually provide you a little bit voltage drop that enables the turbine to speed up as current increases. However, it does not provide you the opportunity to match all the optimums of the power curves. So, by the way, we can see that the maximum power curve has a direct relationship with the cube of the rotational speed. This is then that would allow us, if we could control, the torque or the speed of the turbine, and we know this data, this K optimal, either by having tested the wind turbine before and measuring this data, or either by having an online optimization program that would actually guess that that number, that k-ops. You could actually use torque control, so calculate the torque at t+1 based on the square of the rotational speed multiplied by k-ops. And for speed control, there is another relationship. So how can we control either torque or speed? There are two possibilities. One option is one power architecture. Could be a DC to DC conversion. So Martin Jäger from LibreSolar just presented such a solution. And all the challenge would be to actually control the torque with the current that's drawn by the DC converter. But we still have this, with this architecture, we still have these losses in the diode. We still have these harmonics. So another way to do it would be a three-phase inverter topology, controlled in certain ways, in such a way that the speed of the generator or the torque could be monitored. So the game is to control the opening of the switches according to the desired speed or torque by using field-oriented control method, which is a modern way of controlling motors. However, this converter is not free of constraints because it's a boost topology, which means that the DC voltage here must be higher than √3 times the AC peak voltage here. So in some application, like battery charging, low voltage battery charging, it would need to have a DC-DC converter here to adapt and to charge the actual battery and to maintain a constant voltage on the DC bus. The advantage of this method is like a much more smooth switching behavior. So we have tried this only with this power architecture at the lab and on the test rig on a small machine, only with a resistive load here. By the way, we have also diodes here that are not represented because they are internal to the MOSFET. And so here is the small machines. So it's 0.75 meter. It's a low voltage generator, about 12 volts nominal speed. And here are the first results. So the green power curves are measured with the inverter topology with field-oriented control, and the red curves are measured with diodes. So overall, we have an overall gain in terms of power of 10%, and peak gain of power about 15%. But this is not fair comparison because on the field, it's not possible to obtain the red line operating points with the diode rectifier with direct battery connection with fixed speed, because we would have like these operating points as I showed before. So these results are, we think, interesting to exploit, and would like to try at higher power. You can see here it's only 18 watts of power. So we are currently building a test rig to a 700 watt test rig to see the results at higher power. The next steps of the project is to control algorithm like fuzzy logic or sliding mode control to be able to guess that K optimal. And we could also implement that then after on a microcontroller and perform on the field measurement campaign to see how it actually modifies the behavior of the wind turbine and and how we could improve the power curves. I would be really interested into having a comparison with the last article about the Scorig wind trials, which actually displays several power curves, and they suggest in the end to change one parameter in the system to see the impact that the element of the system has on the wind turbine power curve, and that could be one of the elements to change. And finally, we could imagine other applications for this, having back-to-back converters for water pumping, and so on. Hope that was interesting, and okay to report to. I'm open to any questions and any collaboration. You can either send an email to me or to Romain. That's all from me. Thank you.
Thank you, Adrien. Great presentation. Do we have any question? Yeah, Hugh was suggesting that the power control must take account of the losses in the stator as well.
Yeah.
I don't know.
Yeah, sure. Sure. This is something to take into account. And if we imagine application where we would using high voltage DC for example for DC inverters that can accept high voltage, then we could design high voltage stators which with less losses. But yes, obviously in the parameters, the control for the machine, the stator losses should be taken into account.
Yeah, you should take it into account, because even if you go at higher voltage, then your winding will have a higher impedance. So for a given mass of copper in the stator, you're going to have the same efficiency in terms of copper loss.
Right. Thank you.
Well, thank you, Adrien, again. Luis, I think the floor is yours for the last presentation of the panel. Luis, I think you are muted.
Yes, thank you. I was just sharing my screen. Can you see my presentation?
Yes.
All right. So thank everybody. This has been a very, very interesting few hours. I'm very excited about giving you this presentation because I actually spent the whole night last night preparing it, because I was trying to think of what could I actually say. And the best way to do this is trying to sum up. What I'm going to say is basically, I'm going to synthesize what we're all saying in a certain extent, because that's part of what this presentation is about. I've been working with, I'm working with the concept of software-defined power converters, and we're going to look at that into detail, how to make a multi-purpose equivalent of a power processor. Before we start, I am still young, associate professor at the University of Toulouse. I've been researching electrification and power electronics at my laboratory for the past 6 years. For those of you who don't know me, I've been an active member of Wind Empowerment and the board since 2014. And I built about 15 wind turbines. Actually, I've built the test rig as well in my lab. And I've been working on open source power electronics ever since 2014, when I started my research. Now, I am a scientist. This is important because it's kind of my job to think up stuff that's complicated. At least that's how people see my job. But science is about modeling things, which means we observe stuff and we try to come up with an explanation why things are the way they are. And technology is about making things, making artifacts, making things work, right? So this presentation will be a mix between science and technology. I will start by the science. Let's take it first a step back. Look at the big picture. Then I'll dive deep into the technology to talk about our project, the OwnTech project. I'll explain before that what are software-defined power converters, what's the concept behind this. And then I'll take a second step back, which means I will do another scientific abstraction for you guys. But the purpose of this is not, there are absolutely no equations on the presentation. It's just conceptually speaking, what I've been working on and how does it justify in terms of pursuing these ideas. So let's start by what we know. Power. Power is current times voltage, which means we have a nice chart whose area, any point in that chart is a power, right? Is a watt. So let's give us some leeway here. Let's trace two hypothetical lines, 50 amps and 100 volts. If we look at that, that kind of sound like arbitrary limit, but actually we find a lot of applications that correspond to those limits. That means small PV, small wind, small batteries are going to be below 100 volts. Beyond the 100 volts, we're going to very quickly come up with inverters, single phase or three phase. If we go beyond, in my case, I put 50 amps, and we are at that very high voltage. I just said that's Joker, that's the grid. And we have the sort of, I don't know exactly what you put in that case. So I just put medium PV and a medium to large storage, which basically means it's a system that's grown too big and the people have not yet put the PV models in series. So we can go back to that, but that's not the point today. So if you look at this chart, we can actually do the very interesting exercise to put into this everything we've spoken about so far. So we can start by the greatest contribution, Piggott. Again, thank you for your wind turbines. Everybody loves it, and you've inspired a lot of people to do better. So we start by Piggott's turbines, right? We put them on the chart. We have a lot of small Piggots. I put a 1 PV panel just as a reference, about 40 volts. Maybe the panel could be a little bit higher, maybe 5, 8 amps, but still. This is not totally T-scale, so indulge me a little bit. So you have all these different designs. I put the diameter and the voltage. So we have these small voltage, and we have big Pigott. I called it big Pigott. So it's the 3 meter, 3.6, and 4.2, which are, at least in the manual in French, they are all wound for 350 volts because they inject a single phase into the grid. So that's what everybody loves about Piggott. So you kind of live into two worlds, and then we can add, difficult to see, but OSWACC is there just below 50 amps because at least I saw in the website is 45 amps, 12, 24, 48 volts. We got LibreSolar with a 20 amp and a 10 amp. I kind of squeezed them in there in the middle somewhere. And I went into another website to look at 1 kilowatt battery chargers, not charge controllers. They're actually chargers. They charge and they discharge batteries. They are active chargers, right? So I put them there to give us a reference. Then we actually do have DC motors, industrial DC motors. I put small DC motors there. There are a bunch of DC motors which are below 100 volts. We have 1 kilowatt DC motors, which go up to about 180 volts. And we start to find a single phase inverters, which are near to the biggest turbines, which is the big Pigott. And we have 3 to 10 kilowatt solar inverters. I put a bunch of them because it's different currents, so I just pile them up, which is the kind of stuff you find on SMA. And if we push this a little bit further, we are gonna get, to the 30 kilowatt plus solar inverters, which are a little bit off on the right. We have medium AC motors with speed control. So speed control here are 3-phase inverters, which control the speed of these motors. So I just put them together, the motors. I thought it was easier to do that. And they're all up there to the point. I put 800 volts. They could be a little bit less, but that's the voltage that these inverters need in order to control these motors. So what you see is a very quick panorama of what we've been talking about. A lot about the small wind, and then things get big and then they get complicated, right? But there is a hidden thing, and it's a hidden thing for absolutely every one of you. And I want to point that out because this is very important. There is a function behind this. I'm sorry, it's impossible to connect a wind turbine to a battery. You have to go through a rectifier, active or passive, doesn't matter. So that means that you need a conversion function. You need to go from AC to DC. That sounds obvious. Of course, it is obvious. But rectification, the rectification goes into all the wind turbines. There is DC to DC, and that kind of showed up in many different. The OSWACC is a DC to DC because it's actually converting DC voltage into and dumping into the load. It's a DC to DC converter. We do have battery chargers. In my example, I put the LibreSolar charge controllers there in DC to DC. I put the small DC motors there just to cut something like, to kind of put something in the middle, otherwise it would be two completely different worlds. And we'd have DC to AC, where we are inverting. So we go single phase, three phase, and go all the way up to the power. And what you see here, and this is very important, we do power electronics, and I've done it as well, so I put myself include, as people done electronics in the 60s. Basically, what does that mean? That means that we find a function and we make an analog design for that function. So, okay, there are microcontrollers, what you're talking about, Luis, no, just abstract. We associate hardware to function, to conversion function, which means that we are kind of stuck to the problem that as soon as you kind of want to change your application, the function changes with the application and your hardware is kind of like obsolete or it doesn't adapt anymore. So how do we go from doing electronics like we did in the 60s with op-amps, with transistors, to doing electronics how we do on the 80s, on the 90s, on the 2000s, and now, which basically means integrate and make the equivalent of a power processor. So I call this soft power because it kind of goes, soft power. So it's a software-defined power converter. It's basically you go from that idea that you design based on your function, and you abstract from that, just like we did with microprocessors. We abstracted the whole thing, and we said, if we could reuse this, if this could be a sort of common ground for many applications, not all of them, because it's impossible to cover them all, but some of them, how do we do this? We found solutions for microelectronics, but we have not yet found solutions for power electronics. And that's what I've been working on for the past 6 years. Now, if I simplify this, which is a big simplification, there are only two ways that the scientific community has found to do power electronics: digital power electronics, software-defined power converters. There are two ways. One is to do like an FPGA. For those who don't know what an FPGA is, it's not a microprocessor. It's a circuit that you reroute it physically through a software. So you use the software and you say to your circuit, this is how you're going to be rerouted. And it's sort of like you have the function, but it's a generic circuit, and you reprogram it, and you can reprogram it as many times as you want. I actually supervised a PhD thesis on this, but with people who are way more competent than me, who have been working on this stuff for 10 years. And the idea here, if we bring it back to our chart and our abstraction, is I trace the red lines with the 50 and 100 volts. We just forget those lines. We forget whatever everybody has ever made, and we just cut a module. And the idea is that we associate them in series in parallels, and we reach whatever power we want. This approach is basically the equivalent of you give your specifications to someone, and 2 days later, they provide you with the power converter. That's automated design. It's not necessarily reprogrammable. That means it's not necessarily providing people with a computer, something that they can reuse and reprogram. You're providing them with a solution off the shelf, which is in a few weeks, it's operational because you got the technology for it. This is interesting. It's going on. These guys in Grenoble are working on this. They're very competent. They're maybe going to break through this in a few decades, but this is hard stuff. There are a lot of complications to it. This is not what we have done in OwnTech at LAS. What we have done is we said, let's take the approach of a microprocessor. So a microprocessor, it's quite distinct from an FPGA because you make some choices and you make some compromises, and in the end you got something that does a lot of stuff, but not everything. For instance, a PIC 8-bit does a lot of stuff, but not everything. And if you want more, a better, maybe digital to analog converters, analog to digital converters, some better DCs, maybe you got to invest in another chip, another reference, and so on. You make choices and you make a product that kind of fits those choices. So basically is what we have putting that back into power electronics is that we looked at the chart and we realized there is a locus of low voltage power. There's a gap in the middle, and there is a locus of high voltage power. And you cannot operate on all of them at the same time with the same power converter. So we split the problem into three. One of the three solutions are on the right, but I'll explain it right now. We have a low voltage inverter, equivalent of an inverter. It's actually the solution that you got from Martin, from LibreSolar was talking. Sorry, just got blank. Sorry. The solution he was explaining, which is basically a synchronous buck. But if you put them in parallel, you got a low voltage inverter. So you have this block, which is low voltage. You make it for low voltage applications. Then you have an isolation transformer. Now, transformers are usually bulky and big because they're 50 hertz, but if you put them at 200 kilohertz, they become very small. So this is an isolation transformer that is operating at 200 kilohertz, which means that it is a fraction of this volume of a normal transformer. And then you have the third block, which is the high voltage inverter, which operates at the high voltage and can deliver the power at that level of power. So if I go into the detail, I dive in a little bit better, a little bit further. On the left, if this is too complicated, just remember yourself that the light green and the dark green are exactly the same thing, but at different voltages. So one explanation for one will solve the other. This is a low side synchronous buck, for instance, on the left. You have a V1 low and V1 low 1 and 2. We use Romans for the low side 1 and 2, and then Arabic 1 and 2 for the inputs. You have two legs in parallel. These two legs actually provide you with the possibility of doing DC to DC or DC to AC conversion, in this case, a single phase. The idea here is that this is bidirectional in current. It means that you can boost or you can buck depending on your application. I can go back to the details later. We added a little MOSFET on the bottom because if you're doing AC, your neutral has to be disconnected from the ground, but if you're doing DC, you need to connect them both. So that's how you do it. In the middle, you have this extremely high frequency, 200 kilohertz transformer, which makes, all of these are 10 by 10 boards. Maybe the dual active bridge will be a 10 by 16 centimeter board, and it will allow us to boost the power. So boost the voltage from the input to a voltage that is high enough that we can actually make an inverter out of it. And then you have the other side, which bucks the energy down, and it can make an inverter out of it. So if you look at the detail, on the left side, so you have these two legs. We have to start somewhere. So we told ourselves we're not going to start by doing the equivalent of an STM32 because that's way beyond our pay grade for now. We'll start doing the equivalent of a PIC microcontroller, something simple, something that will work, and something that will cover a lot of interesting applications, but not all of them. So the left side, this is the board that we have designed so far. We're starting to test it. It's a 300 watt, 12 to 80 volts on either leg on the low side input, and it boosts up to 60 to 90 volts. So you have, say, anywhere between 12 and 80 on one side and anywhere between 60 and 90 on the other, boosting the voltage up. And you can go up to 60 amps at the specifications that we have today. You can use it as a charge controller with one leg or two. You can interleave the legs, which means it can boost the current. You can use it as a bidirectional battery charger, which means you can actually control the current of your battery and put an algorithm onto it. And you can use it as an active rectifier on the future version where we're going to put 4 legs instead of only 2. Because there's a sweet spot when you interleave a lot of legs, 4 is about the optimum. We measure voltage and current on each one of the inputs and on the high voltage bus. That means that this is de facto a data logger. We measure voltage and current to control the power converter, and we actually average these values, and we can send them up and observe the system. This is important for the next steps. The orange stuff in the middle is basically a galvanic isolation. So if you actually have a system that is within a voltage that can that requires that galvanic isolation. This is what you're aiming for. It will separate, it will split the locus into two, and it will be safe to operate on your low voltage while you're attacking on the other side as well. So it goes from 60 to 90 to 350 to 450. Why? Because on the high side, we have a single phase inverter. So if we put 3 of them in parallel, you can do AC motor control, or you can do a grid tie one-phase inverter. So these are the functions that we can do with the same triad of power converters. That means that if you are operating on the locus of small wind, you don't need to go all the way up to the high voltages. You can just use the low voltage part. But if you need to go and control some high voltage machines, because these machines are pumping water, then you can pile up the blocks. What's our digital architecture? Well, each one of these blocks has its own microcontroller that is controlling its power flow. And they send the data up to a more powerful microcontroller, which actually has a state machine, and it's actually controlling everybody else. It's giving them the references that they have to follow. We have an embedded a real-time operating system into it. It's an open source real-time operating system. It's kind of similar to the Zephyr that we were talking about before, but it's a slightly different. We adapted it for power electronics. So basically, what's in the dashed green line, it's kind of like the expert area of the project, and the people interact with it either via an intuitive interface and a programming intuitive interface for whoever is trying to code the new applications, or just through a simplified data interface, which will communicate with what we call ThingsBoard. ThingsBoard is it goes a little bit with Erni was doing. It's a system that gets the data from the backend firmware and throws it into a server, and you can actually munch that data later. So our objective is to unify power electronics. That means that we're going to have standard hardware, but that's not enough. We're going to have an intuitive user-guided interface. Why? Because with this, you have a bunch of libraries, you click and point, and you just put your parameters in, bam, your converter works with the libraries that we're going to provide, the open libraries that we're going to provide. There's going to be simplified IDE for those who actually need to develop their libraries, because we cannot do everything, but we'll provide the most important ones. It will have open data monitoring, which means that you don't need to have a data logger for a specific part, because if you have these power converters everywhere, then you're data logging the whole of the system. Ideally, we'll have one community, a lot of people working on this, and a unified documentation, because it is so hard to do power electronics whenever you're dealing with power and industrial electronics and data and so on. Who do we target? Again, this is not just for the end user. We talked about this before. We target skilled individuals, people like us, who are makers or entrepreneurs who want something that is easy to use and whose price is not prohibitive. That's where we're aiming for. We're also aiming for small companies, maybe large companies, but who knows, who need to have a quick product into the market, so they get it and it works, and need support for the functionalities. And we are actually targeting academics who need reconfigurability and actually something that is cheap. And what we're going to offer the people with this project is a single hardware software suite with a unique price. So each power converter will have its own price, but they will have their own price. Usually when you need something custom in power electronics, it's a nightmare to get a pricing on it, because it's a service and it's complicated. And it will be sold online, probably not by us, probably by some company that's going to make it. And we're maybe going to make a foundation and just keep the development going forward. Who knows? And for the businesses, we could actually offer them, if you guys want to build your own system, we can help you out with that. Timeline for the project is now we are in November, it's end of November. The V0 of the 3 blocks is going to be complete somewhere between end of January, end of February, somewhere around there. So we're going to have that V0, and we're going to start testing it during the winter, and by beginning of the spring, we would actually send some of these out for people who want to test them. We're probably going to create something, so companies, association, whatever, we're going to create legal structure somewhere in the spring. And We want to actually iterate with people. So it means we want to talk to people, get them to test, get them to burn what we've done, so we can actually integrate their solutions into the V1 of the converter, which will be about the end of the project now, but we'll probably fundraise somewhere in the middle and keep ourselves alive. So this is the technique. And I want to take another step back, but I'm going to do this short. This is short, but this is important. We talk about energy a lot. We talk about, everybody was talking before is finding ways to tweak the system so that you put different things together and you kind of find a balance between the different parts. So I call that energy balance. But energy goes with information because you kind of get measurements and you act with some sort of automatic control. So you do have an information balance. It means that if you lose that information, maybe your system goes afoul because you're needing to measure and monitoring the system to control it, to observe it and control. But if we go away from the technical side, there is a financial balance that needs to be found, because if whatever you provide to people does not give them productive activity, well, they cannot actually have the money to reinvest the financial investment that is required to keep it running. So it has to bring them something. But there is a link there in the bottom. If you have a financial balance and you have access to the data from your information balance, you can actually upgrade your updates. We're talking about pay-as-you-go. It's typical pay-as-you-go, but it could be other types of applications. But there is not enough. There's a last thing that was missing. This is one of my PhD student who is doing this. Is a model that he cooked up a few weeks ago. We're working on it. It's a social balance. That means that there is some sort of social investment into the technology, and there's some sort of social return. And the data is actually provide people with the means of social control over the information. And people collect payments for the system that they're using. Somehow they have to pay for it, and that goes back in salary. So there is a flux. This is a systemic view of a microgrid. And if anything of this goes awry, the whole thing falls apart, even if the technological solution was great. So why am I saying this? It's because there needs to be a social balance mechanism. And that's, we use it in our project through openness. Because if you have access to knowledge, you guys all know this, and you have access to technology, you can actually act. You can know and you can act, and you can do that locally, and you can change the system. You can understand the system. I'm not talking about necessarily the end user. I'm talking about the guy who sells a system, the guy who makes a profit or makes a company selling and making a living out of this. And that's why we do use open source licenses, because open source licenses allows people to have, the people who are living off of this, to have control over what's going on, to provide the means of getting it, making it better, repairing it, making it more reliable. So we've chosen open source licenses to everything in our project: the hardware, the documentation, the graphic user interface, even the dataware. Everything is open source. It's like a sandbox where people can communicate, exchange, work together. All of this is hard open source. That means that whatever changes are made on the sandbox is for everybody, but people can ask, on the side, make their own project if they want. If they think they can outrun everybody else, it's fine. The objective is that people are free, but the sandbox belongs to everybody. So we have a community space, we have a Discord channel, we have a GitLab as well. We are going to create a YouTube on the spring once we start testing our power converters. And when you put the whole thing together, if you have the power converters that are flexible enough to act on different elements of the system, and you have the information system that is open and allows you to get all the data that you need, and you actually have a data system that you can program parameter and make some sort of pay-as-you-go equivalent billing system that is adapted to your context in your society. And the whole thing is actually sustained by a company. You have all the levers that you need to correct that flow of balance as it goes. And this, my friends, is a PhD thesis that's going on right now in our laboratory. And the guy doesn't even know, because I don't think he connected all the dots yet, but I connected it yesterday in the night when I was doing my presentation. all of this is not just some bullshit for some scientists out of nowhere. We've been working on this for a few years. One of the very interesting things that we've done, I wanted to put this here, is that we went to Glasgow to test some of our power converters. On the upper left corner, you're gonna see a lot of people. There is me and Alfie. These are the only two people who are totally useless in that photo. Everybody else, there was Jacobos from N2A from Athens. There was Antoine, which is my PhD student. There was Guillermo, who is presenting us before. And there was Jean. And every single one of them was developing a different algorithm using the same hardware. So if you look at the center photo, you see Jean and Guy trying to use the same hardware to drive a brushless synchronous motor and an asynchronous DC 230 volts motor as well. And we actually made them run. Well, we burned the boards, but we made them run in the process. We made, if you take a photo on the right, is the inverters that were doing the three-phase inverting that we're testing as we were there. But there was more. Last year as well, we had the chance here in Toulouse to assemble our mobile microgrid that we've done with Gilou. It's basically a shed, a small garden shed where we have batteries inside. If you look a little bit to the left, there is on a diagonal, those are amorphous silicon PV panels that Gilou has. And laying on the floor is actually the tower of the wind turbine, and we raised it, as you can see it on the right. And this photo on the left, this is a little message. It's you see our OSWACC on our microgrid. So we do have a charge controller, and you see a green power converter. There's actually a second one hidden behind my laptop. We had two power converters, exactly the same topology that was presented by LibreSolar just before. So you guys, if you need a power converter, we have one. Exactly the same, but 8 amps, not 20. So we can talk about the size of the inductor. On the left, the power converter was actually running an MPPT on the amorphous silicon. So I put the MPPT program onto the power converter. And the same power converter on the right, I put a fixed duty cycle because our battery system was 24. And the inverter, the blue thing on the sitting there with which I'm charging my cell phone, is actually a 12 volt to a 330 volt Chinese inverter. So we had to adapt, and we used the power converter to do that adaptation. So that kind of proves a little bit of the concept of this reprogrammability into different circumstances. And that was a quite interesting solution that we did. And thank you very much. I'm very, very happy to be here. Very happy to have done this presentation. And, you know, if you have questions, please go ahead. I'm here.
Thank you, Luiz, for your presentation. I don't see any questions, and I think we are quite late on the schedule. So I propose that we move on to the next presentation. Unfortunately, without the time for discussions inside of the panel. It was a pleasure having you all from the power electronics side, and I think it was really a good follow-up on the charge controller session panel, because we really had a lot of different views on how to improve our ways of controlling our wind turbines, which is, I think, a hot topic in wind empowerment community, and which should lead to more collaboration between us and more follow-up between the panelists as well. I believe it's a great way to improve our systems. Now I would like to hand on the floor of speech to Ludwig from Erni kollektiv in Germany, who will present something completely different, which is related to water pumping applications. So yeah, I think Ludwig, the floor is yours.
Yeah, thank you. Hello. Just gonna share my screen. Yeah, there it is. Can you see it?
Yeah, it works.
Okay. Do you still see the control panel up there? No. Okay, well, let me start just saying something about myself and the group I was working with. Yeah, I started studying mechanical engineering, but I didn't finish because now I'm doing an apprenticeship to become a metal worker. So I'm more a practical guy, I guess. And yeah, in 2019, I was building that 3F turbine back there together with a group of students, metalworkers, and engineers. But most of them were like, yeah, spending their free time and also their pocket money for the project. So we aren't professionals, we are like just enthusiastic. And yeah, we knew that small agricultural site next to Rostock, the place where we're living at. This is a solidarity agriculture. That means that they are selling their foods directly to people and not to a supermarket. And this is like a small field of 1.5 hectares. And they don't have access to the grid. So they don't get water and electricity power supply. That's why they ask us if we could like build a wind turbine and a small PV system for them. And they got a 20-meter deep well, which they're running, or which they were running with a like fuel generator. So yeah, we started to build a wind turbine. We checked the wind there. We got data from ERA2, and because we're next to the coast from the Baltic Sea, we got like a theoretical wind average speed of 6 meters per second. I guess it's a little bit lower, but that means that's useful to have a wind turbine there. It makes sense to install one. And so we got this 3F, and I think it's like 700 to 800 watt wind turbine and 20 volt system, together with about 500 watt solar power, which are actually old solar cells, so they might not be good enough. And also the batteries are from the scrapyard. So I don't know if they still got the 200 ampere hours, just like which they should have. And on the other side, we got this 300 or this 3 kilowatt inverter and the 750 deep well pump. And yeah, we put this together, and we got this pool, which is storing the water for the gravity drip irrigation system. It's about like 40 square meter, 40 cubic meter of water could be stored there. And yeah, we put the system together, as you can see here. Yeah, it should be, yeah, you should know how it works roughly, but let me explain some additional things, like with the wind turbine there, it gets rectified and stored in the batteries together with the solar panels, which have their own charge controller. And in addition, we got the Arduino we programmed ourselves, which is which should control the damp load via the MOSFETs. They are still burning all the time, so I'm gonna switch to this charge controller Adrien was showing to us today. I'm gonna install that one, I guess. And yeah, on the other side, the Arduino is controlling an AC relay to control the pump, if it's running or not, and a short circuit break for the wind turbine in case of like grid loss of the Arduino. It's fail safe, so if the Arduino doesn't have power anymore from the batteries, so if the battery is disconnected or anything other is happening, like overspeed, the wind turbine is going to be short circuited, just a safety aspect. And yeah, on the additional, the Arduino is measuring the battery voltage, the wind power, wind rational speed, like the RPM, solar power, and the power output from the batteries. And yeah, we got lots of information from that project from Philippe, also from France. He made an MPPT regulator with an Arduino. From there, we got like all the information about how to build a sensor for the rotational speed and the current sensors. So thanks to Philippe. He was also asking questions from us, and it was really helpful. And yeah, we are switching the pump depending on the battery voltage. As you can see here in the diagram, if the battery voltage reached the 27.9 volt, then we switch on the pump, and we switch it off at 23 volt. So it's always oscillating. And as you see, this isn't good for the battery at all. Like the battery is really not well charged. And that's something we really need to improve. For example, just to switch on the pump if the battery is well charged. But yeah, what you can see is that like the higher the total power is, like the green line is the solar power, the red line is the wind power, and the purple line is the total power. Like the higher the total power is, the more often the pump is switched on, which is the orange line. If it's like at 1, then it's the pump is pumping actually, and 0 it doesn't. It means it doesn't pump. And therefrom we get like we define the pump ratio, like the time that it's on compared to the time that it's off. And in total, we get like over the last summer, like it's working since last spring. And we got a total power input average of 101 watt and a pumping average of 12%. And here at the diagram, you can see like the ratio between the power input and like the average pumping time over 6 hours. So like the more power you get, the more time it's really pumping. And this yellow circle is like the average where you're working at. And yeah, with 12% of like pumping time, we get 5 cubic meter per day of water. Like if you take this times 24 hours and 1.7 cubic meter per hour. And that would mean that we couldn't get like enough water for the whole land, for the 1.5 hectare, but it was enough to water the greenhouses with the tomatoes, because they got like just 750 square meter, and there we get like 6 millimeter per square meter, which is enough to really water tomatoes. And that also makes sense because this is like tomatoes got the highest profit margin in our town or in Germany compared to the other fruits he's growing there. That's why we like first support the greenhouses, like in communication with the local farmer. And yeah, but to compare our system with other systems, I was taking this this plot was published by Jen in the technology forum. This plot shows actually like the expected flow of water compared to the total head on the left, as you can see, and the mean wind speed for a 4.2 Hugh Piggott wind turbine. And we got like actually the 3 meter wind turbine, but we got 500 watt solar in addition. So I was just take this to have a rough comparison. And there you can see that at our field, also again, the yellow circle, like with 25 meter of total water head, which contains the like the real difference, the high difference between the deep, the well and the pool, and the dynamic like pressure losses in the pipes. So we have like, we should have get 20 cubic meter per day with a mean wind speed of 5 meter per second. And we actually got 5 cubic meter per day, which is much less. So there should be something to be improved. And like so I was looking at the advantage and disadvantage of the way we are using the power right now. And like the advantage of our system is that we can combine the wind and solar power by using batteries. And we also could use the energy for other tools and lighting by just taking them through the inverter from the batteries. But like the disadvantages are that we are losing power while battery charging, and also in the damp load where the power is converted to heat. And we are losing power in the inverter because it's working like all the time, not only when the pump is really working. So there's also like 25 watt all the time converted to heat. And we don't have an MPPT regulator installed yet. And yeah, these things brought me these things brought me to the idea of focusing on direct water pumping, because I saw this this diagram, which I just wanted to show you, where you can also see like on the x-axis, you can see the rotational speed of the turbine, which also controls the frequency of the current. And on the other axis, you can see the power that is being produced. And yeah, you should know that kind of diagram where you can see the different wind speeds and the potential power that you could take out with your wind turbine. And on the other side, you have two different curves of other pumps. One is the piston pump on the right and the centrifugal pump. And there you can see that the centrifugal pump fits much better to the wind turbine because they all, both of them got like the power is related to the third square of the rotational speed. And if you just plug them together, that should be work quite fine. Like same like an MPPT regulator, you always got like the optimum load to your wind turbine. And yeah, other advantages of the direct water pumping, you can see on the right that you don't need batteries and you don't got charging losses. And in the end, you don't need to get rid of your old batteries. So you have less hazardous waste. And you don't need power electronics at all, except some regulators, like for getting the turbine started, like no load at the beginning, low wind speeds. And yes, I said the centrifugal pump works as an MPPT regulator. So like the further steps for me would be to improve the battery charging by installing this OSWACC, as you call it, and probably building a generator for direct water pumping for that site. Also that we like, and to use the PV panels just for lighting and for other tools. And maybe because I'm just learning to be a metal worker, I'm also interested in building the so-called Western mill to pump water just mechanically. And there's also a group in Germany who, that is like designing this Western mill, and they have built already one. And that's also interesting for me because I know how to work with metal. Yeah, that's all from me. I'm Ludwig from the Erni kollektiv in Germany. Yeah, thanks. Nice to present this to you, and I'm open for collaboration if you want, like testing some data, and yeah, thank you.
Thanks a lot, Ludwig. I love your feedback on my graph that is obviously a bit false. Well, let's try to find the problem then. Also, I believe we may have to discuss a bit further, not now, but the assumptions behind this graph and try to spot the problem, because these are huge differences in flows. So
yeah, I realize.
But I love it. Seriously, it's great.
Yeah, thanks. Are there any questions about that? Okay, well, so you may continue.
Loic, I think it's your turn.
Okay, let me activate the microphone and share the screen. Thanks, Ludwig. Very, very nice. I love it. Wait 2 minutes. Okay, can you see my screen now?
Yes.
Okay, all right. So hello, everyone. Thanks for the invitation. I'm super excited to be here to discuss about our project. It's called Turning Sun into Water. And even if it deals with solar energy, I'm pretty sure that most of the things that we have learned in this project can be useful to turn wind into water as well. So this is the outline of the presentation. I will start by recalling the motivation of my projects, and then I will say a few words about our installation in Burkina Faso. And then we will talk about modeling and optimization. And finally, I will try to summarize the contributions to date and open up with the perspectives. So let's start with the motivation. We are studying water collecting systems in rural areas in sub-Saharan Africa. And basically, there are two main types of systems. The first one is the one with rope and bucket on an open well. And the second one will be a hand pump on a borehole. These two systems, they are very popular. You can find them quite easily, but they are associated with some problems. And these problems, they directly impact the quality of life of the user. For example, the difficulty of extraction. Difficulty of extraction can lead to back pains. Bad water quality can lead to diseases. The distance that must be traveled between the source and the household carrying the water can lead to a waste of time. And above all, the cost of water directly impacts the purchasing power of the user. So there is today already a competitive motorized solution to this problem, and this is photovoltaic water pumping. You could use wind water pumping as well as a motorized solution. But this is only a technical solution. And the question is, does this technical solution actually resolve all the problems encountered by the user? For example, it might be easier to extract water from the well, but the user still needs to carry out the water between the source and the household. So at the end, what is the impact of the solution on the quality of life of the user? In other words, what is the socio-economic impact? And this is the underlying question that we are studying: how to assess, how to quantify this impact, and if possible, would it be possible to design a system in order to maximize the positive impact? So for us, photovoltaic water pumping is not only technical, is not only a technical problem, it's a problem that is technical and socio-economic, because the user is at the center. So there is a relation between the design of the system and the performance. And basically, this is what you will find in an electrical engineering lab. People in electrical engineering, they will try to design a system. So it means they will try to choose a sizing and a position in order to minimize, for example, the life cycle cost. But there is a second component to this whole system. This is this second part here. This is a link between performances and impacts. And this is typically what one would study in a humanities and social science lab. And what they will do is actually look for a relationship between a given performance and an impact, for example, to start a socio-economic impact. And this is this relation, these two relations that we try to study and to link together in the same program. And this is why, this is what motivated us to work together with these several labs. So the two first labs, JIPS and SATI, they are laboratories of electrical engineering. This lab here at Stanford University is a lab of hydrology. And then at Imperial College, we have a lab of humanities. And in Colorado State University, we are working with some people working with econometrics. So the project started by installing a photovoltaic water pumping system. And the goal was to collect data so that we can calibrate our models. So this is our installation. It was set up with the help of 280 backers through a crowdfunding campaign. The system was installed in Gogma in Burkina Faso, and it provides now water to 200 inhabitants for their domestic consumption. The system was built in end 2017, and since then, it is in operation. This is the architecture of the system. We have PV modules that are feeding the motor pump with power. The motor pump is inside the borehole and is pumping water from the borehole to the water tank. And the user is fetching water at the fountain. In the tank, we have a float switch, which measures the water level in the tank, and it will stop the pump when the tank is full. In our present case, in Gogma, the tank is 11.4 cubic meters, and we have only 620 water peak of PV modules. So it's quite a few. for 280 inhabitants. A lot of data have been collected before, during, and after the installation. For example, we collected GIS data. In this map here, the blue points, they represent the GPS coordinates of all the concessions, and the red, orange, and green points, they represent the various water points in the village. In addition, we carried out water household surveys, and the aim was to understand better the consumption habits of the inhabitants before and after installation. And finally, we monitored the system since its installation. To monitor the system, we built our own data logger. And this data logger is measuring the irradiance, the ambient temperature, the temperature of the PV modules, the voltage and the current of the photovoltaic modules, the pumped flow rates, and the collected flow rates at the fountain by the inhabitants. This data logger is autonomous with its own PV modules, its MPPT, and its batteries. And this is an example of the data that we measure every day since 2018. This is the data of February 19th, 2019. And for example, here, this first graph here is the irradiance as a function of time. So it's a sunny day with few clouds. And the second graph here is the temperature, the ambient temperature here, and the PV module's temperature here. So we can see that daily temperature reaches 40 degrees. Here, this is the pump flow rate by the pump in the borehole. So the morning, it starts with the sun. I have some pumping, and when the tank is full here, it stops pumping. Here, this is the water level in the borehole. So you can see that when we start pumping water, the water level in the borehole is decreasing. And when we stop pumping at this moment, the water level is going up in a logarithmic fashion. Here, this is the voltage and the current of the photovoltaic modules. You can see that the current is following the irradiance, and the voltage is going back to the open circuit voltage once we stop pumping. And this one here is the consumption flow rates by the inhabitants. Basically, each spike corresponds to the opening of the tap at the fountain, and we have 3 taps, so we can see if the users, they are using 1 tap, 2 taps, or 3 taps at the same time. So the second stage of the project was to build this technical and socio-economic model with the goal of optimizing it. And the model is made of 4 subsystems. This is the first subsystem. It's a technical model, and it's been validated by comparison of the measurements from our data logger. This is the measurement of our data logger in red, with the model's output in blue. And we observed that we had an error of less than 5% over representative periods, both for the dry and the wet seasons. So we consider that our model is valid for this system. We also demonstrated that it was possible to replace the data logger measurement but by satellite data. This is here, satellite data. And by doing so, we only need the position as model inputs, but we lose 3% of accuracy. The second submodel is an economic model. Basically, what we did is that we collected costs from the local Burkinabe market, and we made fittings in order to estimate the CapEx and the OpEx of the various elements of the system. For example, here, this is an example of the CapEx, so the purchase price of the photovoltaic panels as a function of their sizing. And here, this is an example of the CapEx of the tank as a function of its volume. The third model is a demand model. The goal of this model is to predict the demand of the photovoltaic water pump after installation, but it only uses data that have been collected before the installation. And the fourth model is the impact model. It is a model that makes it possible to quantify the socio-economic impacts by comparing the situation before installation to the situation after installation. So let's go back to our problem. What we want is to link the design with the performance and the impact. For example, we want to link sizing and position to costs. and cost to socioeconomic impact. And this is exactly what our model does. It makes the link between sizing and position to the costs and the socioeconomic impact. So this is the third stage of the project. It was to use this model in an optimization problem. The optimization variables are the position of the system, the latitude, the longitude, and the sizing of the system, more specifically, the sizing of the solar panels, the volume of the tank, and the reference of the motor pump. We have two objective functions. The first one is to minimize the life cycle cost, and the second one is to maximize the socioeconomic impact. And I show you here an example of the optimization results. I'm going to plot the life cycle costs as a function of the socioeconomic impact. So these are our two objective functions. What we want is to maximize, is to minimize the cost over the life cycle. We want to minimize the costs. We want to be here. And we want to maximize the positive socioeconomic impact. We want to be here. So to summarize, we are looking for system in this area. And this is the results for several motor pumps. For a given motor pump, we obtain a set of points with one color. For example, this one. And if we look at all the points that are located at the optimal position, they are actually located on these blue lines denominated optimal. This is a Pareto front. And we can see that the two objective functions, they are contradictory. Basically, you have to pay more if you want to get a better impact. You have to pay more if you want a better impact. So where is our system now for the moment? Where is GOGMA's systems on this curve? Well, it's here. It's here. So it's not on the Pareto front. It's not on the blue line. So it's not optimal. Actually, what we can see is that we could have obtained the same socioeconomic impacts, but we could have paid much less. Indeed, the current sizing is well oversized. And to achieve the same socioeconomic impact, we could have used a much smaller solar panel, a smaller motor pump, and a smaller water tank. By doing so, we would have saved $8,000 on the installation. There is an interesting fact, is that the set of optimal solutions, that is to say, the set of sizings that are on the Pareto front, they are actually inside this green rectangle. And interestingly, the current system is here. It's in the middle of this rectangle. This means that the chief of the village, who actually chose the location of installation, chose, in that case, a quasi-optimal point. So now I want to try to summarize what we have learned that could help us solve the problem of water access and what we can do in the future to solve this. So we think we have three types of contribution. The first one is on the photovoltaic water pumping systems. We monitored continuously since more than 2 years the photovoltaic systems in rural Africa. And from our point of view, from our knowledge, this is unique. And if it gives you any ideas, please contact us because we will be happy to share this data. Then we proposed and validated a technical model for the photovoltaic water pumping system. And by doing so, we learned a few stuffs. We learned that it was possible to use climatic satellite data without losing too much accuracy, and that it was possible to use only a 1 hour time step. And so it's good because it reduces the constraints in terms of monitoring. It's going to cost less money to monitor that kind of system. The second contribution is more on the methods. Basically, we proposed a new optimization variable, the position of the system, and we proposed a new objective function, the socio-economic impact. And we coupled the two models, the technical model and the socio-economic model. And finally, in terms of water access, we established a water demand model. This is a model that predicts where the household choices and the load curves. And we propose the theory of change that is behind, that makes it possible to quantify the socio-economic impact. And to conclude, I want to show you the few perspectives that we have on this project. What we want to do is to study the long-term impacts of the installation. indeed, the installation was installed in 2018, but the lifetime of the system is 20 years. So we are only at the beginning. We think that it will be very interesting to study the long-term socioeconomic impact at 5 years, 10 years, 15 years, 20 years, and to study the long-term environmental impact, especially on the hydraulic resources. Finally, we could use these two long-term impacts and take them into account in an optimization process. If you want to learn more about the whole project, the Turning Sun into Water project, and other projects about solar pumping, I invite you to participate to the solar pumping workshops that we are organizing. The event starts on December 9th, and it's going to be free online with very nice presentation about solar pumping. So feel free to register and to join us on that event. That's it for today. Thanks.
Thanks a lot, Loic. Amazing presentation. I loved the project. Just a quick question from me. The local universities were not willing to participate?
In Burkina Faso?
Yeah.
So we have been in contact with them when we went for the installation, and we helped, we actually collaborated with them on other projects at that time,
okay,
but not on this one.
And so you choose to keep out of the scope all the supply of the equipment of the impact, or like how did you handle the situation of bringing some technology? I guess the funding was local, or it was coming from the project, or you brought the technology and evaluated the impact. But I don't understand this point. How did it happen? You brought the prototype?
So when we say impact, we say socio-economic impacts. I'm not talking about the impact of transporting the goods, if this is what you meant. So we are not. It will be more in the environmental impact if you want to look at the impact of transporting goods and of buying goods. But this is not what we have been doing. We have been looking only at how the installation is changing the quality of life in the village.
Okay.
Does that respond to your question?
No, the question I was asking myself is how you can put a quantity on the evolution. Like it clearly depends on how you bring the system. For instance, if you bring the system and you make the villagers part of developing the system, for instance, and size the system themselves, it will have a different social impact rather than if it's designed by a team in France and proposed as such for the villagers.
Yes, totally agreed. So what I want to emphasize is that this is an academic project. And in that case, we only observed what an installer, a local installer was doing in Burkina Faso. The installer is called Dagatech. The money was coming from a crowdfunding that was then used by Dagatech to buy and install the system. This one. But we actually did not design the system. This is a local installer that designed the system.
Okay.
Okay. So we actually, as a French laboratories, if you want, we did not choose the system.
Okay.
We let the local installer do as he would have done alone. And basically the choice of the village, it was done by the installer because it was asked by the village, and the dimensioning, for example, of the village, the location of the pump in the village was chosen as it's done there normally. So it was really interesting to learn how it's done. So basically it's the chief of the village that chooses from a geophysical measurements, because you still need to have water on the ground if you want to pump. So we only observed. We did not design it. We only observed how it's going on. And we use the data to calibrate models so that we can maybe later in the future have tools to help for the decision for the chief of the village, or at a more global level, at the regional level, or even a national level.
Okay.
But I totally agree that the way the village is included in the decision, in the whole process, is very important for the sustainability of the system.
But now I fully get it. I fully get the way you did it. I completely understand.
Yeah.
And Katrina is asking, how do you measure the change in quality of life? What criterion do you use? And thanks for the interesting presentation.
Okay, so I'm going to share this screen here to show you a little bit more how we do this estimation of socioeconomic impact. Sorry, it did not work. Okay, so this is just an example to show you how it works. This is our impact model, the socioeconomic impact. It's a little bit more complicated, but this is just to explain how it works. We consider this household, and we consider two situations before installation, so before the implementation of the photovoltaic water pumping system. For example, this household was using this open well to collect water, and this open well, actually the quality is quite bad, and the quality is quantified by the number of coleoforms per unit of water. This is this number, okay? So basically 380 means it's bad water, and if you drink it, you are going to be sick. To go to that well, the distance was 170 meters, and the price was free. Actually, it was free to use that well, okay? So this is the situation before installation. After installation, the habits of the users, they change. And for example, the quality is much better because with the photovoltaic water pumping system, we can pump much deeper in the aquifer, so the water is much better quality. So in that case, we say that we have 0 coleoform per unit of water, so we have good water. If you drink it, you are not going to be sick. In that case, the distance was a little bit shorter. It's only 80 meters, but it could have been more. It could have been much, much more actually. So it depends on the household that you consider. But to use this water point, you have to pay this time. You have to pay 500 francs CFA per month, okay? And so basically, this is what we are looking. We are looking at the delta quality, the delta distance, and the delta price. And in front of this delta quality, delta distance, and delta price, we are using coefficient alpha, beta, gamma that makes it possible to sum these quantities, okay? And then we sum this on all the households. This is the situation for one household, but you sum this on all the households of the village because you want to compare for the whole village, okay? And this is how we obtain the socioeconomic impact. So for example, in that case, the socioeconomic impact will be a quantity between 0 and 3, okay? Between 0 and 3 because we have 3 delta. The big question is, how do you choose the coefficient alpha, beta, and gamma? This is the biggest question. And basically, this is not our job as technicians to choose it. This is more a choice from a political point of view. Let's say you have money to invest in Burkina Faso at the state level, and you want to invest money in a region to make water pumping. This is your job to choose if you are going to favor water quality or to favor distance or to favor price, okay? It's more going to be a decision maker that is going to choose these coefficients. So I hope this explains a little bit, this sheds a light on how we calculate this socioeconomic impact.
Well, thanks a lot for this explanation. I think it's giving a good glimpse on how it's evaluated. I believe we now have to give the floor of speech to Esteban Van Dam, who will present.
Thanks.
Who will present the project that is running in Argentina around productive uses and water pumping, and that will close this panel about water pumping.
Okay, thanks, Jean, and hi, everyone. Hope you can hear me. Please let me know if you can see my screen so I can start. Is that okay?
Yes.
Great. Okay, so thanks, everyone. Great to see so many familiar faces in this meeting. So I am co-founder of 500 RPM. We started this NGO 10 years ago, and we've been working in wind, mainly in wind developments, in small wind developments in Argentina, and also in the region. So we've worked in Chile and Uruguay, and recently in Mexico and Dominican Republic. So we've been working in projects in different countries in Latin America. Mainly developing projects, small wind projects. And since water pumping has become a very demanding solution, let's say, in many places, we've started working on this almost 2 years ago with the project of the SEPS project, together with Jean in France and Jorge team in India. So what I'm going to share is how this was evolving over the past year or so, in our case in Argentina. So basically, what is the need of small wind in Argentina? We are focusing in the southern region of our country, which is Patagonia. This is a very windy area. Rural population are very scattered. They are very isolated. And they have been recently migrating, slowly migrating from cattle, which is the main activity there, towards agriculture, which is way more economically attractive. Cattle has had a lot of problems lately, especially with very low temperatures and snow storms in winter. A lot of animals have died, also with volcanoes. Issues in the past years, so agriculture has been growing interest in the area. It's very desertic and very arid and very windy. So this is a very good combination for small wind, and this is the reason why we're focusing here. So what we're working on is basically drip irrigation. This is our main target. In many places in Patagonia, there are rivers, and people will mostly live nearby a river. It's not always the case, but it's many times the case. So water does not need to be taken from deep wells, but rather from a river that's on the surface. And then the typical configuration is that the water is pumped from the river towards a tank in height, with enough difference in height so that the pressure then by gravity is enough for drip irrigation, at least 5 meters high. So what we've seen there is that with one small wind from Hugh Piggott's design of 1.8 meter rotor diameter, which is mainly 350 watts nominal power, you can irrigate around 2,400 square meters in this area where it's very windy. So it really does have it's really a technology that makes sense in this area. And drip irrigation has a high added value. We are mainly focusing today in strawberries production, which is the one that has the best added value, but most people in the area have different production, so they don't just produce one thing. So even if strawberries is the one that looks more attractive, it's probably going to be a mix. So what is the technical solution around on our end? We've been using a brushless motor, which is an e-bike motor. It's used for bikes, so we didn't invent it, we didn't manufacture it. We just use one that is easily available in the market. And we combine it with a diaphragm pump. Main advantage for this pump, and I will come back to this later, is that it uses variable speed, so that it's easily you can still work. It's not an on-off situation whether it's running or not. It's more it can run at different speeds. So depending on the wind speed that you have, you can have it running at different speeds, and then you need a specific controller for that. So our initial configuration was, as you can see, the wind turbine with a rectifier feeding through this specific controller the brushless motor, and that was powering the pump. The problem with this configuration, which was sort of a MPPT controller, is that this controller did not react quickly enough for the speed of variation of wind speed. So basically, it stopped all the time. We had too many stops of the motor when wind started going down, and then when it went up again, it took some time before it started running again. So it had a very important hysteresis losses. So this was not an optimal configuration. And even though our original goal was to avoid batteries completely, we finally abandoned this idea. One of the reasons why we abandoned this idea, that I go back to the previous slide just for a second, is that the wind turbine is not only feeding drip irrigation solution for household in the middle of nowhere in Patagonia, but also household needs. And most of the people that we are bringing these solutions and that we're talking to, they don't just need water and energy for irrigation, but they also need water for their household. So ideally, we would have to bring a solution that will help them with both things. So that's why having a battery is not such a bad idea after all. But if it's only for drip irrigation, we actually don't need a lot of batteries. So the idea is that we only use a very small battery bank, which is used for buffer rather than for storing storage or storing energy. So this having been said, we abandoned this. I mean, we didn't completely abandon it, and we're still working on it. And ideally, and eventually, we might have a solution for this in case some end users might need a solution that is only for water and no need for household. In which case, maybe a solution without batteries is still possible, and we keep working on this with John and with Guillermo Catuoño from University of San Luis in our same country. But we have now switched our short-term priority towards a solution with batteries. So how does this work? Just to go back for a second to the solution. So this is the pump that we're using. This is a diaphragm pump, which, as you can see up here, it says N 180 RPM. That is the nominal speed of the pump. But if you're half that speed, basically you have half the water flow. So it's not, again, an on or off situation, but you can use it in a broad range. And it has quite a good water flow for up to 10 meters height. This is probably not very good for other places where you need to bring the water from people else, but it is in these areas where we're working where we're taking water from the river. So this pump has a good efficiency at variable speeds. It has a good efficiency for up to 10 meters height. And it's very robust and very commonly used in Patagonia. This is very important. So we're not bringing a new technology that nobody knows, but we're rather using a type of pump that people are used to in the area where they can find easily spare parts and so on. So what we are changing right now is a little bit the logic. So we still use the same brushless motor, we still use the same pump, but we changed a little bit the controller, and we are introducing batteries after the rectifier. Not a big battery bank. The idea is just a small battery bank initially. That will depend on the needs of the household, which are separate to the water pumping needs. But essentially, if it's only for the water pumping needs, you don't need a lot of batteries. And these are only for buffer purposes. And we have a new logic, which I will comment later on. But then the same motor is powering the same pump, basically. So this new logic has this general architecture. So we have the wind turbine. Through the batteries, we have a first level of control, which leads to a second level of control with powers which, let's say, rules the motor, which powers or moves the pump. So I'm going to share with you these two levels of control. So basically, the first level of control is basically like a PWM controller. But with some add-ons, let's say. So the inputs are the battery voltage. We also want to know the temperature, basically, because in Patagonia we can have temperatures below zero. So we want to know that the water has not frozen in the tank. We have a float switch signal to let us know where the tank is. And we have a timer, which will be used for the logic of stages of charge of the batteries, which I will comment later on. And the outputs of this first logic or first control level is basically one binary value, which is either C or D. So this only tells us whether the battery is in charge mode or in discharge mode. So basically what we say is that batteries are going to be charging for a time until a moment when they reach full charge. And from that point on, they go to discharge mode and they start discharging until they reach a minimum, and then they start charging again. So this is this kind of evolution, let's say. We need to know all the time whether if we are in a charging situation or in a discharging situation. We will have a relay to break the wind turbine, so for the free phase to stop the wind turbine. We will have LED for failure codes so that we can know which problems there might be in the wind turbine. This helps a lot when we want to do maintenance in remote areas. So at least local people who maybe don't know a lot about wind turbines, at least they can read some LED lights and have some quick information about what might be going wrong, so that when the maintenance team goes to the area, they already know what might be going on, and they bring the spare parts for possible failures or most likely failures that are happening there. We have a relay to disconnect the motor in case we need to stop the pump, and there is a PWM basically for dump load to reduce that. So this is the first level of control, and then this leads us to the second level of control, which runs the motor. How does the second level of control work? Basically, again, we need to know whether we're charging battery or we're discharging it. So if we're charging, basically, as Hugh commented first in his presentation, battery will start with a first stage where it will reach approximately 60 or 70% of state of charge, where the voltage is going to grow to this level. And then you need to start reducing the current that you're bringing to batteries, and the voltage of the batteries keep growing but slower, and then you are between 70 and 100% of state of charge, and you are in the right axis. You can see you are between this type of battery. This changes from one battery to another. This is just an example. You go from 13.6 to 14.8 volts for 12 volt battery. So basically, what we have decided is, since batteries are a big problem and we don't want to use them a lot, we want them to be always above 70% of charge. So if they are below 70% of charge, we simply don't run the pump and we don't use it. And if we are between 70 and 100, if we are in charge mode, if we're charging the battery, we are in this voltage. Now, if we are discharging the batteries, we are in these voltages, which are very different. So maybe we have reached, I will go back to the previous one, maybe we have reached 14.8 volts for one battery, or 29.6 for a 24 volt configuration, typical configuration. And after that, when stops or is reduced and voltage starts going down, and as long as it hasn't reached 12.5 or 25 volts for a 24 volt configuration, you're still in above 70% of state of charge. So only when you reach this value, you stop the pump again. So the voltages that you use as reference are different when you're charging or when you're discharging. So this is what the second control does. It looks at the battery voltage and it looks at whether they are in charge or discharge mode, and this comes from control 1. And then, based on that information, they will tell us what the speed of the motor will be and what the acceleration, so whether it has to grow and at which speed it has to increase the speed, or at which speed it has to decrease the speed, so the acceleration of the motor speed on and off. So this is what the second control will do. And this is a typical table that we are using today. We are only starting these tests, so we might have to move these parameters, but this is based on the tables from the battery manufacturer. So basically, when you're charging the battery, as long as you're below 25 volts in a 24 volt battery bank, the motor speed is 0. And this is a percentage, what we're seeing here is a percentage of the nominal speed of the pump. So we don't use the pump at all if we're charging battery and it's below 25. So we wait until the battery has reached 25 volts to start using a little bit of pump, but we only run it at 10% of its nominal speed. So we only use a very small amount of energy on the pump, but we do pump some energy with this voltages until 27.2. Once the battery goes above 27.2 up to 28 volts, we run the battery at 50% of its nominal speed. When it's between 28 and 29, we go 75%. And only when it's above 29 volts, we use it at 100% of its nominal speed. Now, when it's in discharge mode, the battery has already been charged. You can use it for much longer. So when it goes down to, we wait until it goes down to 25.6 before we reduce the speed, because that's when it reaches 90% of the voltage. So the fact that whether it's being charged or discharged is very relevant. So these are the main parameters that we're using. And this is a simulation that we have from a time series of battery voltage that we have in our test site in Buenos Aires, where you can see how voltage changes over time. And this is only simulation, so we haven't tested it yet. We are programming it right now. We hope we can start our tests next month. So basically, as here the battery voltage is too low, we're not using the pump at all. The red figures are at the pump. So once we have reached this value and the voltage starts going up, at some point we start using the pump first at 10% of its value, then at 50%. Then the wind starts going down, the voltage is reduced in the battery, so we go back to 10% and then back to 0, so we stop the pump. And then the wind starts blowing up again, so we go using first 10% and 50%. And only here, when we have a long time, 2 days in a row, this is a week more or less. So 1.5 days in a row with very good winds and battery fully charged, then we are running the pump at 100% of its speed. So this is the logic that we are targeting right now. So for conclusions, the batteries as a buffer makes the system way more robust. Most people need power for their household too, so in most cases we will need batteries anyway. We always keep batteries above 70% of charge, so we make sure that we don't cycle them too much and that they will last longer. Household needs in winter and irrigation needs in summer. So we have, at least in Patagonia, we have this configuration where household will need more of the energy, most energy in winter because of the lights need, whereas irrigation is mostly needed in summer, so it compensates. And that's why having battery for let's say, holistic solution is a good idea anyway. Basically, the configuration is one small wind, 1.8 meter diameter. That helps us, or that will be enough for 2,400 square meters for drip irrigation. Knowing that basically one family consumption is around 100 square meters, so the rest is for marketing, for selling. And the results from simulation say that we should have an average of 5,300 liters per day, which is what we need for this surface in this area in Patagonia. So, of course, we need to test it, but this is what we have obtained from our simulation. So, our next steps, we expect to finish our controller design by the end of this year, and we can test it in our test site in Buenos Aires in the first months next year, between January and March 2021. And then that we can bring it to Patagonia for field implementation somewhere in the first half of next year. That's it. That's our Facebook from 500 RPM and our website. And happy to hear your comments or your ideas. Thank you very much.
Thank you, Esteban, for this presentation. You have a question from Adrien. And he is asking if in your simulation there is a feedback loop between what you take from the battery voltage, from what you take from the battery and the battery voltage you are measuring. So basically, as soon as you will try to extract power from your batteries, the battery voltage will, of course, reduce. So how do you take account of that in the simulation? Is it the case or not?
Yeah, in the simulation, we simply took it as a percentage of reduction. So we did take into account that, but without we are not sure that the parameters that we used for that are what we are going to get in real life. So this is very tricky to simulate. So we only used it as a percentage basically, and we cannot do too much more without having test sites, and maybe it doesn't make sense to go too deep into simulations when actually what we want to do is what happens in reality. So our target is to this was only to have a broad idea of what we would have, but now we are quite advanced in the programming of this controller, so we expect to have our first results within a couple of months.
There is also another question from Loic, who is asking, what is the local temperature and does it impact the battery state or the health from your experience?
Yeah, we have to protect the batteries, so we cannot have them outside because in winter you can have -15 in some areas. So it depends on the area where in Patagonia we're going to, but you can have very low temperatures. So batteries are always, every time we have done an installation in Patagonia, we put batteries inside the household or in a place that is kept warm, let's say, because you cannot leave them outside in these areas.
I'm just sending a link around in the chat, in which you can find the first socio-technical assessment that we've done during the first phase of this project. So it's available for download on the website. So you can have a bit more details on how we planned the first version of the system without the batteries and how it slowly changed. And you can find the curves that Ludwig was mentioning that seems to have a small issue. So this is what we've done during the first phase of the project. And now, hopefully by February, we'll have the second phase completed. And Adrien is asking if we compensate the threshold with temperature. So basically, if we plan to integrate the temperature estimation of the battery in our algorithm.
We should. I mean, to be honest, we haven't started yet thinking about it. We do have temperature as one possible input of water, but the temperature from the water, not from the outside for the battery. So as long as we have the batteries inside the household, this is not very critical. Although of course it always improves the control. But maybe we will have to do that in a second stage. We should start thinking about it. But yeah, in a second stage, so that we don't tackle all the problems at once, and at least that we validate that this is working as a broad model.
It will be super interesting to see it tested.
Yeah, we have the data logger installed on the same site, so we hope that we can have some very useful data that we can share with everyone as soon as possible. Not only, I mean, water flow data and voltage data, but also current going or amps going to the battery or wind speed, and also RPM from the wind turbine. So we want to measure all of these parameters together. So hopefully we will have some valuable information to share with everyone. So that's the goal.
Well, thank you for these wonderful presentations for the water pumping panel. We may take 5 minutes more to answer a few more questions if there are, or to discuss a bit between the panelists. But I think the technology session extended itself a lot. and the 10 minutes time slot obviously was wishful thinking. So yeah, I really hope that at some point we will manage to have more collaboration between our different projects, because I sincerely believe that we have complementary projects, and it would be super interesting to share you some data that we've collected on the socio-technical impact, for instance, Loic, and to see if we can extend a bit what you've done in Africa to some other cases. It would be great to see if there is a possible match on that.
It would be awesome to apply it to a wind pumping system, or to any actually productive use of energy, of wind energy. It will work.
Especially that wind is a bit specific in the fact that it doesn't apply everywhere in the planet, but only in windy places that are kind of special, or in place where PV cannot fulfill the needs of the watering needs or the productive uses that are intended by the local citizens. So yeah, I believe there is a really good connection between the two projects. And also with you, Ludwig, I really I'm amazed by your homemade system that you've built with your friends. It's really great.
Super exciting. I want the same.
Yeah, and, thank you really much, because I'm I don't feel like I'm expert, right? Like I'm professional. We just did like read a lot of forum, Googled a lot, and just put together what we found. And I think there's a lot to be improved, but yeah, it would be awesome to get information from you or tips. Anything is welcome.
But actually, you showed us some really nice graphs with the pump switching on and off and the battery states. That's super interesting.
Yeah.
So great job. I mean, that's a lot of work.
Thank you. Yeah.
And if you want to have a chat at some point for the mechanical pumping turbine, I mean, because at some point I had a hard time trying to design a mechanical pump that was not working with a regular piston pump, but rather with a centrifugal pump. So basically, you keep the tip-speed ratio of the wind turbines that we have, but instead you make a mechanical collection with a spinning rod to act on directly on the centrifugal pump. This would be awesome. I would love to finally try it.
You were building in Morocco, you told us before.
Yeah, but it failed dramatically because I didn't take into account the 4 degrees angle in the Piggott design. So
yeah. Give another trial, maybe. Yeah.
But what they do in the States with these low spin wind turbines to pump water is like incredible, and it works for years and years without stopping.
Yeah. Definitely, but the only problem with the slow spinning wind turbines is that if you put them in windy places, they tend to break quite easily.
Of course, it's not made for. But it's actually quite good with a piston pump or.
Yeah,
but you need to put them directly over the well, so you can't put them on the windiest side, like you're fixed to the well where it is. That's another disadvantage.
Location is very important.
Yeah.
Yeah. Well, guys, amazing discussions. I think we can wrap it up here. And of course, we can stay connected. And I sincerely invite every one of you to join the next session on next Saturday on delivery models and market assessment, because I think it will have a lot of echoes to what you've presented today, Loic, with different works by amazing panelists as well. Thank you for this amazing presentation again. Let's keep in touch, and in between we can work on the hackathons proposed by Luis and Adrien.
Great, thanks for the invitation, and see you next week.
Cheers.
All right, thanks everyone. Bye-bye.
See you guys.
Bye.
Bye.
See you. Bye-bye.
Have a good night, afternoon, I don't know.
Bye-bye.
Good night, guys. See you.
See you in the sessions.
Bye.
Thank you for organizing, Jen. Bye-bye.
I guess everybody's gone. I missed the end.
Are you still there, Luis?
Yes, I had to put the kids to sleep, so
Yeah.
just.
Yeah, I think most people are gone now. They all said goodbye.
I'll stop recording. I think we should stop recording.
Probably. I wonder if Hugh is still listening.